I request ସମସ୍ତଙ୍କୁ ହଲ୍ରେ ଡାକିଦେବି ଅବିକା ହଲ୍ରେ ସମସ୍ତଙ୍କୁ अशोक कुमार मिश्रा. I request everyone to please be settled down in the auditorium. This one I'm using, yeah. I would now request our jury member for this session, Professor Dr. Ashok Kumar Mishra, to please come upon the stage. Welcome back. Hope you had a delightful lunch. With that pleasant interlude behind us, we shall continue with today's program. Ladies and gentlemen, now it is my privilege to introduce a truly distinguished scientist, Professor Himanshu Shekhar Vishwal, Professor at the National Institute of Science Education and Research, NISER, Bhubaneswar. He completed his MSc from Utkal University and earned his PhD from TIFR, Mumbai, followed by postdoctoral research at CEA, Saclay, France, and the University of Michigan, USA. Joining NISER as a DST Inspire faculty in 2012, he rose to professor in 2022, establishing himself as a visionary leader in spectroscopy. Professor Vishwal's research spans laser and synoptical spectroscopy, polaritonic chemistry, vibrational strong coupling, and tetrahertz spectroscopy. His remarkable contributions have been recognized with the Sierra Psi Bronze Medal, Fellowship of the Royal Society of Chemistry, and numerous prestigious awards. Today, we are fortunate to learn from a scientist whose work pushes the boundaries of molecular science. It is truly an honor to have him with us. Everyone, please join me in giving a warm and enthusiastic round of applause to Professor Dr. Himanshu Shekhar Vishwal as he presents current advances in vibrational spectroscopy and instrumentation, exploring molecular frontiers. Thank you.
Right.
Okay, so there are very few students. Before I start, let me thank the organizer, Professor Abani Sahu, for inviting me and giving me a chance to talk over whatever. Mostly I'll talk about the instrumentations we did to do the optical spectroscopy at NISER. I'll give a summary. I don't have time to explain actually whatever we have done. Okay. So my respected teachers, the students, friends and colleagues. So before I start actually, why I am here? I am here because of few teachers. So I'll share one slide. Okay, so what I am talking about Professor Balaram sir. So he is so inspiring. Whenever I met him in 2021 in Baripada. So after that we are in great touch actually. Always whenever I publish something, find something, I share with him. He also shares with me. So he has lot of interest actually to visit our lab, and last annual OCS annual meeting he told I'll come and I'll go there to visit your lab. A message though, that message I wanted to show, and unfortunately he could not come, and I went there also to the city to receive him. He was not there, and I was planning to take him in during puja vacation, and unfortunately he passed away. So this is the message actually he wrote, and this is what, after discussing with him, I shared in the social media about the teacher. Mostly I share about my teachers, my students, about in the social media. So he had a lot of wish. Actually, I cannot take all of you to my lab, and if you are willing to do so, you can come to my lab to Niger at any point of time. I will be there, or my students will be there to take you to show the what is called the laser spectroscopy, how the spectrometers are built. So we have built many spectrometers, and you will have a flavor. Okay, so I need this one. Give me. So this is what I am not advertising. We belong to Department of Atomic Energy, and again we belong to HBNI, Homi Bhabha National Institute. This is our university, and recently all are going through this NAC, all the stuff, and they share a slide to us to share whenever we are giving the talk. And I belong to Niger, and this is what some of the photo I have taken from Niger website. Give me. No, I don't need, but I have to change now. Synchronization will not be there. I'll go there then. Otherwise, stand here. Okay. Is it possible to bring the laptop here? Anyway, it will be very difficult. Anyway, go back to the beginning. Yeah, okay. Yeah. So let's start. Next slide. No, next. Yeah. So let me thank, actually before I start, let me thank my students. So it is the effort. I don't want to take any credit. I just guided as a teacher. They have put the effort. Even if today I am not here, they will be there in the lab. Even if Saturday, Sunday, I don't ask them to come to the lab at 9 a.m. or something. They will be there in the lab. So I thank, before I start, I am really fortunate to have the students from almost all part of the country. So I have contributions from 14 PhD thesis, 29 MSc thesis, and that I am going to summarize in 25 minutes. Please next slide. Okay, so since I told I will give a vibrational spectroscopy, which is bridging the gap between the disciplines. I will tell how the vibrational spectroscopy is useful. Already you have heard about the NMR and the fluorescence spectroscopy, and that will make my life easier to explain what is vibrational spectroscopy. As sir said, Sudhang said, it's an absorption spectroscopy, vibrational spectroscopy. So what is molecular vibration? I have categorically I have put the S2S dimer here just to show something called the intermolecular vibration and intramolecular vibration. So the intermolecular vibrations, the bond stretching, covalent bond stretching, it comes in the mid-air region, and this is the top spectrum, and the intramolecular vibration, it's come in the terahertz region, about 100 or 300 wave number to 1020 wave number. And if you have a dimer, you will have 6 intramolecular vibrational mode, and it's very easy. So dimer we treat as 4 atom system. If you take 3n minus 6, then you will have 12 minus 6 normal mode of vibrations. That is what is represented here. Next. Okay, so next. So I will tell these are the questions we ask and we know. So, the lifetime decay curve is exponential. It could be bi-exponential, it could be mono-exponential. Is it possible to have exponential curve? You have ups and downs. So, in simpler language, I call it ups and downs, and this is actually called the beat. Okay. Next, which is related to a physics problem. Next one. Yeah, so we know in our high school or 10th class or 11th class, we know the hydrogen bond can be possible with electronegative atoms. So, either OH or NH with oxygen, nitrogen, fluoride, these are electronegative atoms. And is it possible to have hydrogen bonding with sulfur, selenium, even tellurium and polonium, the electropositive atoms, and that is related to the physical chemistry problem. The next one. Yeah. So, we use to have the enantiomeric excess, we use chiral chromatography, sometimes they use chiral agent and use the NMR spectroscopy to find it out. And is it possible to have vibrational circular dichroism, which we are developing, and to have the enantiomeric excess, or is it possible to have a H2S dimer or H2S trimer or tetramer? H2S is achiral, right? Do you agree with me? Hydrogen sulfide. So, but is it possible to have the dimer, trimer, chiral? Okay. How can we get to know those? We will get to know from the VCD spectroscopy, that is related to organic chemistry. Okay. So, as I said, as Sumanta started this one, the catalysis. The catalysis, you need to have a catalyst to lower down the energy barrier and to have the reaction faster. So, can I do the catalysis without a catalysis? So, that is what called the recently developed technique called the polaritonic chemistry or vibrational strong coupling, VSC. Next one. So, we have these are the questions we are going to ask, and these are the disciplines they are going to answer. So, there are expensive time domain terahertz spectroscopy, and people are talking about the femto spectroscopy. You need a femtosecond laser to have the terahertz spectroscopy in time domain, and do you know how much it costs to have? It is about 10 to 12 crore, okay, to have a terahertz setup. We have one in our physics department in Niger. And can I use my FTIR spectrometer, which is a bit cheaper, and extract the many parameters related to the time domain data using the frequency domain data. And also give you few examples of material science, how they can use our method to find it out the optoelectric properties. Next one. Okay. So, single crystal XRD gives information about the molecular architecture. Okay. So, I will give few examples how the frequency domain terahertz spectroscopy can be used when you not have a proper crystal or your molecule is liquid. Okay. So, how you can do? That is one problem JP sir gave me to find it out the diastereomers, which is not a crystal. Okay. So, it has lot of relevance in biology and inorganic chemistry. LPT. I am wasting time. Take. You click. Okay. So, yes, that's fine. So, this is the simple example. I started with SO2. So, I started my PhD in TIFR. I started with NMR theory. So, I worked 2.5 years, and there was some conflict between the guide and the student. Then I left and joined in the laser spectroscopy lab. So, in the laser spectroscopy lab, this is the molecule I started, the triatomic molecule, and I recorded the lifetime data for triatomic molecule, only one molecule. Okay. That is a technique I am coming to. So, I repeated this experiment 2 to 3 months without telling my guide. Okay. This is what I am observing in the lifetime decay. I always thought in MSc all the stuff, the lifetime will be exponential. Why that is beat? So, there is a beat actually when I went and read actually the beat is because of the there are two. All the laser has a width also, okay, in terms of wave number or wavelength. So, even if we were using the very narrow laser width, but it is good enough to excite 2 rotational levels at a time. So, one of them we have electronic excitation, you have a rotational also at the same time. So, like this one, I excited the molecule here to here, okay. Then there is one rotation level, it comes back to the ground state. At the same time, because of the laser width, there is one excitation here to here, okay, that was populating, the other one is depopulating. So there is a equilibrium, and you have a one is decaying, other one is growing up. So you have a quantum bit, and there is dedicated spectroscopy for that. It is called the quantum bit spectroscopy. Do you know, it's not simple. I said we were detecting one SO2 molecule. So if you take the SO2 vapor here, this is a very broad spectrum, and we recorded this one is called the supersonic jet spectroscopy. This is the peak, and if you can zoom it, you can see how many spectrum you can get it, okay. So that technique I am going to explain what is called the supersonic jet spectroscopy. Next slide. Yeah, so this is the instrumentation part. I don't have time to tell. I have a 5 minutes video. I recorded how we do record the spectrum. Okay, so we shine the light if it is a solid. This is called the laser desorption. Then we cool it by the molecular expansion, that is called the supersonic jet expansion. Then we use many laser techniques or double resonance spectroscopy to have the electronic and vibrational information. Next. Yeah, so can you click that video? 1 minute. So we use at least 100 components to build the spectrometer, and these are the components we have used. So we first go and switch on the UPS. This is the sequence of events we do. Then the chiller, then the rotary. Okay, so I am telling how many switch you have to switch off. I am telling one with major components. Then when you have a vacuum pressure about 10 power minus 3, then we switch off the turbo pumps. So how complicated it is, everything we have built and assembled. So this is our rotary, yeah, 10 power minus 3. Then he is switching off the turbo pumps, yeah, T stands for the turbo, yeah. So these are the turbo pumps here. Okay, so we reach minus 6 to minus 7. Then he is switching off the delay generators, which delay generator means it will combine everything, synchronize the laser, the molecular beam, then oscilloscope is switched on. Yeah, this is called the pulse valve generator, which generate the pulses, 10 nanosecond pulses. Yeah, this is how, yeah, this is the how we do the expansion. The expansion you can see he is putting this one. These are the beam chambers we have used, many small beam chambers. Then you have a bigger one where we do the spectroscopy. This is the bigger one. So this one is a fluorescence one. This is the time of flight. The other bigger one is the time of flight. Yeah. So these are the different lasers we have. So he is switching on the YAG laser, which will generate the 1064 nanometer. Okay. So this is the YAG laser. Yeah. So this is we wait for to reach some temperature. Yeah, the YAG laser, the 1064 looks like the white actually. Then we double it and make it 532 nanometer with a crystal, and the green color is that one. Then we use that 532 pump the dye laser, the red is rhodamine dye is used. Then the rhodamine fluorescence, we have optics, we make it double it, then you will have the ultraviolet light. So this is what the high voltage power supply we use to have to record the time of flight mass spectra. These are the mass spectra recorded. This is the IROPO, this is what the optics looks like. Yeah, so the IR you cannot see. What we do, put the graphite one, then we dissolve it. Okay, so you can see the IR is coming. Yeah, this is the REMP, this is we call the REMP spectrum. Yeah, so he is blocking one of them. This is called the IR depletion. Okay, so sir told about you will have a absorption, you will have excitation, then there is something called depletion. This is the schematic, the part we have used many different, and this is the software we have written to write to control our lasers. And this is again another software we have written called Village, and this Village we use to demonstrate to the students how to do the virtual experiment without using the spectrometer. Okay, so this is the village. I generally go to the college and demonstrate that, and everything, all the switches are here. You can switch on whatever a video in 5 minutes I showed. You don't need to touch any of the laser, anything. You can still do the experiment. This is called the village. Okay, so this is all the we form. So we have how many? 6 lasers and many stuff is there. Okay, so I don't have time to go next, yeah. So what happens doing all the stuff, you can see this is a fluorescent spectrum in condensed phase. You can see this one, the fluorescent spectrum, the technique I have used. So we can get that resolution. Not only that, so we have mass selectivity. So you can see we can the temperature without using the cryostat, the temperature will go because of the Joule-Thomson effect actually. This is called the isenthalpic expansion, and we reach the temperature about 10 to 15 Kelvin, and with that temperature you can form the weaker complexes, hydrogen bond complexes, pi stacking complexes, and study the spectroscopy of them. So neither you can do it with NMR. I am not criticizing, I have used all the techniques. Neither you can use NMR, fluorescence, single molecule fluorescence, anything to detect the dimer. This is one of the best technique, only one technique I would say where you can detect the dimer particularly. Okay. Next. So the question, the first question I answered this one. You can have a exponential decay with up and downs, that is called quantum bit. The second question was whether sulfur can form a strong hydrogen bond. If you have a hydrogen bond and if you have a OH molecule, right, if I have a OHY hydrogen bond, if that hydrogen bond will be stronger, the OH bonds vibration will be more red shifted. That is what we monitor. So here I have taken a peptide molecule where you have a NH pi interaction, you have NHO interaction, you have NHS interaction. So if you look at, there is the NHS interaction happens in the lower range, okay, and that is most red shifted. So NHS hydrogen bonding, if I go by the vibrational signature, the NHS hydrogen bonding is stronger, whatever we have observed. So this is one of the proof we have done. We have done many. So there are around 4 to 5 theses on this topic. So next. Okay, so this is again we verified. We did this one with selenium, and selenium also forms strong hydrogen bond. So the way we were thinking, only oxygen can form strong hydrogen bond, it is not true. Why is it so? So if you are a 9th class or 10th class student, you have heard of electronegativity. Nobody talk actually much about the polarizability. If you go down the group, okay, so the atomic polarizability increases where the negativity decreases, right? So it's a combined effect that actually gives the hydrogen bond, makes the hydrogen bond stronger or weaker. It has a combined effect of electronegativity and polarizability. So coming back to Sudhanshu sir's question, I told I have only one example of NMR. I have taken this pyridone dimer, and the other one is thiopyridone dimer. Okay. So in pyridone dimer, if I vary the concentration, one axis is concentration, other axis is the chemical shift. If I vary the concentration, in low concentration the dimer formation is very less, while in the high concentration dimer formation is more. So if I vary the concentration, the proton NMR, the chemical shift increases. Okay, the chemical shift it goes to the downfield. So both, if I monitor the proton, NH proton, both show the similar trend. Okay, if I monitor the carbon one, okay, so I am monitoring this carbon, thiocarbonyl carbon and carbonyl carbon. If I monitor how with the concentration, the trend is completely different. That is what the sulfur can do. Okay, the NHS hydrogen bonding, it is not only strong, it can change the magnetic shielding tensors. These are the theoretical calculations I have done, and this paper was published in AnguChem. Okay, this only one carbon 13 NMR and AnguChem paper, and the referee wrote, he wrote, in my 60 years of career, I have never seen such a, I have never observed actually, notice this change. Okay, next one. Okay, so we did the theoretical calculation to prove that not only selenium, tellurium and polonium can form hydrogen bond. Next. Yeah, next. So now I'll switch actually. Now it was the acceptor, oxygen, sulfur, selenium. Whether I can have a metal hydride to form hydrogen bond. It's not NHOH. It's true. There are controversy. We published this one in 2019. Then there are two JAX paper. They are contradicting each other. The other one by Professor Arunan also. He is just a diplomatic way. He wrote the paper, and none of these three papers cited our paper, which we published for the first time, that metal hydride can form hydrogen bonds. So who is wrong? We could be wrong. The other three could be wrong, or there is all of them theory is involved. Lot of theory is involved. The theory is wrong. So what I found, we are struggling to publish actually the theory is wrong. Okay. So next slide. Yeah. So next, this is the metal hydride we took and proved it. Next one. Okay. So these are the theoretical calculation, looking at the chemical shift, looking at the hydride stretch, all the stuff. Next. Yeah. Where is the problem? Whether hydride has a H minus, or that is the theory is predicting it H minus, in reality it is H plus. So what we did, we took the simple water molecule. Can you think what is the variation of the theory predicting the charge of oxygen in water molecule? You can see. It is this theory, the Loudon is one of the famous theory like molecule and all the stuff. That theory says, okay, the oxygen, the charge on oxygen can be plus. Can you believe it? So we tested about 20 theory using this one, okay, but they are contradicting each other. They have used for different purposes. We cannot generalize it. Next one. Based on this theory, there are two papers came, one in this journal, Organic Biomolecular, another in Chemical Science. I was talking with Satyavan sir today morning. They are telling this methyl group doesn't have a plus I effect, it is a minus I effect group. I didn't believe. We did the gas phase experiment, and we are still struggling. Since you are going to oppose the Western, so nobody is going to accept your stuff. We are struggling to publish, hopefully we will publish very soon. And this chemistry wall, they wrote, time to stop mentioning alkyl group as inductive effect. That's not true. The theory has a problem. It's not who has done the theory. Next. Okay, can you click these videos? This is all about the gas phase. How many minutes, sir? Sorry. Okay, so this one we have built another setup, and this setup we can do solid, solution, gas, any molecule. Okay, this is called the this part is not built. The IR we can go from 10 wave number to 10,000 wave number. We have vibrational cycle-like regime. This is coming actually the ECD and the fluorescent detected CD. So these are I am interested on the chirality transfer. So we are doing that. So we have built this one. These are the diagrams. We can translate this cryostat from here to here. It can vertically move. It can move in the y direction also. So we have this setup to do all the different type of experiment. Oh, this is how it looks like. The real picture is this one. This is how the cryostat looks like. So next. Yeah. So this is our S2S IR spectra at 4 Kelvin. Okay. We have diluted S2S with argon, record that spectra at 4 Kelvin. Then we increase the concentration. This is we can observe the monomer, dimer, trimer and tetramer. This is how the structure looks like. Next, can these molecules be chiral? This one. I said if you take what's S2S monomer, S2S is achiral, right? But the theory says actually, if these are the computed by bidirectional circular dice spectrum. The theory says the dimer has very less intensity. You can see 0.042, and for the trimer it increases to 18. Okay, so there is 300 times increase. So the trimer, the theory says the trimer is chiral. How to prove it? Next slide I'll tell what technique you are going to use. So we are going to use this technique. will have a polarized linear polarized light, then we use the photoelastic modulator to make the circular polarized light. Then we will record the spectrum, we will take the spectrum left polarized and right polarized. The difference of this observance will give me the VCD spectrum. This is what we are going to do to see whether H2S timer will be chiral. If we can prove, and this will be the one of the breaking study, path breaking. Next one, we have tested our spectrometer is working. The VCD has lot of advantage over the ECD. The CD people use the UV one. This is the CD spectrum. This is the VCD spectrum. CD has a very broad band, where VCD has lot of feature. If there is something happen at any part of the molecule, you can monitor using the VCD spectrum. And the other advantage is, in CD you need to have a UV chromophore. Not all the molecules have a UV chromophore, like alanine, one of the example I have given, it does not have a UV chromophore. You cannot do the CD spectroscopy. You can use VCD spectroscopy, you can have the information. And we are trying to find it out an algorithm, how can you increase get the enantiomeric excess using the VCD spectroscopy. That is still working, we are working on it. Next one. So this is the recent study. As I said, I did my MSc in organic chemistry. I have little bit of weakness of doing organic chemistry. This is sir is laughing. So sir used to write the question, I'll write the answer, okay, in the classes. I was good actually in organic chemistry too. So this one we have used, since this paper is not published, the catalyst is very simple, anybody can do. So I have not written the catalyst name. And you can see actually, you can see this catalyst R and S, how they are different, mirror image of each other. The product also mirror image of each other. You can very easily, if the product is liquid, you do not have a crystal structure, I can do the VCD, compare with the theory, I can assign the structure very easily. Next one. Yeah, so it has lot of applications in perovskite, all whatever people are studying. As I said, the other spectroscopy you can do the gas phase, this one has you can do anything in that spectroscopy. So next one. Yeah, coming to the terahertz, what I said, the intermolecular, when I started the intermolecular vibrations, they come in the terahertz region. So people have started using in many, it's a special spectral fingerprint, it has strong absorption by water molecules. So by doing this, you can monitor the biological water molecules. If there is some changes happen, if you have a disease also, if you can monitor the blood, okay, with the terahertz spectroscopy, you can find it out lot of answers. So it is non-invasive, unlike IR heat up the sample, UV damage the sample, okay. The terahertz have very less energy. People have started, it is invasive or non-invasive and non-ionizing properties can be used. Next one. So there are a lot of application. If somebody is interested, you can read this one. Lot of application of terahertz spectroscopy in biological research or medical research. Next. Okay, so what I said, this is what we started with to learn actually. People say urea is a denaturant. You put the urea, it denatures the protein, right? Is it denature the protein? It changes the protein structure, or it denatures or changes the water structures, and the water denatures the protein. So that's what we are trying to understand. It's true, I don't know what is the answer. We took the urea and thiourea, we monitored the terahertz spectra. So it looks like thiourea is doing, there is a lot of change actually. The thiourea is perturbing the water structure far more than the urea. Okay, we are changing oxygen to sulfur only. So that's what we have started, and this is the paper actually. It says it perturbs the water structure that leads to the protein or anything also. It's not, it's a combined effect. It's not only protein is affected, the water is affected, or the biological medium is affected because of the denaturant, because of the drug molecule, and it leads to the some other properties. That's what we are studying with the terahertz spectroscopy. Next. Okay, so as I said, the co-crystal, this is the urea and uracil. You just change a methyl group and you can see the spectral signature. Okay, going from uracil to thiamine, there are a lot of spectral signature using the terahertz spectroscopy. You can use it very cleverly to study the co-crystals also. Next one. Yeah, so I stay there. So as I said, they need us. This is the first paper we published in collaboration with Professor Sanjeev Kaur. So he came to us and he synthesized a ladder like molecule. You have a pi stacking, then in between there is a silver plus iron. Okay. He told, can we find it out any signature? Actually he came for the theory to do the DFT calculation. I told, instead of doing the theory, let's do the experiment. We did the experiment. If you have a silver, you have a peak, this one, okay, and the peak is corresponding to the intramolecular vibration. It gives you the proof that the silver is stacked between these two molecules. Okay, the next one, as I said, they need us for the cut and pi interaction, and we need them metal chemistry for our purpose. So the terahertz, the problem is most of the window, the quartz, the calcium fluoride, KBr, everything absorbs. So you have to buy the diamond. Diamond we cannot buy. You can buy the CBD diamond, which is called the artificial diamond. The 0.5 thickness of I guess a 2 centimeter diameter or something. So this cost about 2 lakh. You include the GST, all the stuff, it will be 2 lakh. And I requested this Professor Oza at Bhubaneswar. He is a polymer chemist. He synthesized a molecule, and we are very nice results we got till now. So here the transmittance is about 70%. Here the transmittance is about 65, but it goes down. We have achieved up to 55%. Another 10% more, and of that size you can get that window within 2000 of rupees instead of 2 lakh of rupees. Okay, so he is doing that. Hopefully he will succeed. Next one. Okay, so this is again we have developed the theory, as I said, from frequency domain data to time domain data, and this one we have in collaboration with Vishnu from Niger. We have done our frequency. This is the algorithm or the theoretical part, the code we have written. So this one we have compared with the TIFR with the time domain data. So the green is the time domain, the red is the frequency domain, and we have almost a match of with them. So this is we are going to communicate, and this will be really useful to the metal scans. Next. Okay, this is called the polyatomic chemistry. We are trying to learn it. So you will have a vibrational mode, then you have a cavity. Cavity means you have a two mirror, and the inside of the mirror are coated with gold, highly reflecting gold, very small thickness. Then when you have we have this vacuum means this empty space, we have lot of electromagnetic radiation of different wavelength. So you make the cavity of appropriate size, then you will have to and fro motion of the wavelength. Then if you have carefully choose the appropriate appropriate length, then there will be constructive interference, and we call that those are the node. So these are the cavity node, these are the vibrational mode, cavity mode and vibrational mode. When these energy matches, they couple each other, and it has a different property. So I have given this analogy. You can have a caterpillar, you can have a butterfly. Okay. So when they in the middle of their change metamorphosis, neither it will fly or it will work. Okay. So the polyton, nobody knows actually how it works. Neither it behaves as a molecule nor it behaves as optical gravity. So this is what we are learning. Next one, these are the design we have made. So it's not. I am telling in a very simple language. It takes months and a year to make the design and test it. This is what we have done, and we have achieved something. Next slide. Okay, so there are a lot of papers are coming up. This is just a 10 years old theory actually applied to the chemistry. Next one. So this is what we are going to challenge this paper. This paper says the coupling means the separation between two peaks is proportional to the extension coefficient, okay, of the carbonate. Here they are targeting this is the vibrator. They are targeting these molecules, and they have very nice correlation. They have very carefully choose those molecules and showed it. Okay, so I don't believe to generalize. I choose one series of this one. Okay, so just to check, you can see they have a positive slope, we have a negative slope, and there is there is no correlation at all. So we have to repeat it. As I said, nobody knows, the quantum mechanics need to be developed. I hope this data will give sufficient input to the theoretician to tell whether this is wrong or okay. Okay, I have to finish. I have very interesting one. I'll take 2 minutes. Sorry, sir. Next. So this is what we have started with metodites. Next. Quickly go. Next. What we found actually, the meteorites. The meteorites. We did the VCD of the meteorite. We find a chiral signature of the meteorite. We did the mass spectra. Try to use our knowledge of spectroscopy and identify that compound. Meteorites, you don't know, it's not organic chemistry lab. You mix two, or inorganic chemistry lab. You mix two salts and find it out. There are many salts, many organic molecules. It was a difficult task for us, and we are suspecting this one. Next. These are from the mass spectra. We have idea about mass. We have computed VCD. Next. So we are suspecting this molecule could be present there. The 5-membered ring, amino acids could be there. Proline type, homoproline type of amino acid. Next. Then, so in theory, we can do computation for few molecules. When you want to screen thousands of molecules, what you do? You have to take the help of machine learning. That's what we have done. I don't have time. Go to the last slide completely. Next. So this is what we learn. Next. So this is I want to say, still hydrogen bonding you can publish in Science. When I started, people laughed at me. What is there to do with the hydrogen bonding? He is my student in Yale. He did MS with me. He published recently in Science. That is again hydrogen bonding. Unfortunately, we don't have this sort, as Sir told. So I have whatever I showed. They have 10 orders of magnitude. Okay. At least 10 to 20 times of those lasers, all the power supply, everything, then you can publish in Science. Next. So this is our recent, yesterday only night I got this one, and this is the first paper will be disulfide, hydrogen bonding with disulfide using this technique. This is yesterday night it was accepted. Okay, next. Okay, so I thank, as I said, so hydrogen bonding is so much of interesting. I still remember this is the last message sir wrote to me. Himanshu, came to know of your article a few minutes back. He wrote in 9:20 p.m. You can imagine a teacher at the age of 94 writing a student like me, okay, at the mid of the night, telling a article few minutes back. Shall go through later. I am having knee breakdown due to a lack of hydrogen bonding. Okay, so I promise I will continue the same till I lack the hydrogen bonding in my blood. Thank you. Okay, last but not least, this is for everybody. So let's thank our parents, including me. I fall in this category, who lacked school degrees but not the vision and will to guarantee us. Thank you all of you for listening to me.
So, any questions?
Where is the mic, sir?
I must congratulate you for the fascinating lecture. I wanted to know, I was quite ignorant, the S2S dimer that you have found out, S2S. Have you done the mass analysis, mass?
Yes.
S2S dimer.
Yes. All of our spectra.
And what about its symmetry? Once you claim that it is a chiral, then you have to also study the symmetry property.
Sure. So if you have a C2 symmetry,
have you put it in any point group or anything like that?
Exactly. The calculation we do. Okay. So these are not symmetric. There is little. We think actually it will be 2 hydrogen will be in the plane. It's not true. One will be up, other will be down. You don't have a C2 symmetry. There is a little bit of bond length.
C2 symmetry must be there.
No. The 2 HS bonds are different. One is hydrogen bonded. It makes it different. There is little induces, but in third one, in trimer, you have a helical structure. right? You can have a trimer like this, or you can have a trimer like this. That's why it is 3 orders of magnitude of the chirality in trimer. Trimer is it? Trimer I am telling, sir. That's what I am telling. The dimer, the rotational strength is 0.04. For the trimer, 3. Trimer, the rotational strength is about 18. So you can imagine it's 400 times more than the dimer. That we are targeting to find it out. Dimer we cannot detect with our technique, but trimer we can detect. We are trying hard. But it's not equivalent. Water, 2 lone pairs are not equivalent. When I was doing that, I was doing the NBO calculation. I'll tell the story. During my PhD, I got to know the 2 lone pair of oxygen are not equivalent. Yeah, so that is called the rabbit ears representation. Rabbit ear, we think the 2 ear of the rabbits they are equal. They are not equal. There is little difference is there. So one is sp3 very close to sp2 to sp3. Another is very p type of hybridization. That I have a paper, very nice paper, water and H2S dimer on hybridization. Very interesting. I didn't know actually. I wrote who developed the theory, Frank Winold. Then he only replied to me. So it's not true whatever you are telling. You go and read this JCP paper. I have that email also.
Hello.
Okay, sir. I'm sorry.
Sir,
Actually.
sir.
Oh, sir.
We have an online.
Oxygen, nitrogen, and fluorine, they form hydrogen bond. How selenium and tellurium, they form hydrogen bond? How it is possible?
Possible. So the polarizability, these are big atoms, right? Oxygen is, see, the electrons are, the outer
Actually,
electrons are bound to the nucleus.
Attention please,
But
attention please. There is an online
I'll discuss, sir.
talk waiting for it.
I'll
We have
discuss,
already over some time. So can it be discussed?
I'll go and sit this question. Okay.
Thank you, Professor Vishwal, for the remarkable exploration of vibrational spectroscopy and the innovative instruments developed at NICA. Your work has clearly shown us how cutting-edge instrumentation can open new frontiers in molecular science. Yes, our sincere gratitude by felicitating him, for which I would like to call upon the stage our jury for this session, Professor Ashok Kumar Mishra, Dr. Abani Kumar Sahu, and Dr. Deepa Nag. Everyone, please give a big round of applause. Moving forward, we are delighted to welcome Dr. Saugata Sahu, an experimental photochemist and assistant professor at the Nano Life Science Institute, WPI Nano LSI, Kanazawa University, Japan. Dr. Sahu completed his BSc in Chemistry Honours from Ramakrishna Mission Vidyamandir, University of Calcutta in 2009 and went on to earn his MSc in 2011 and PhD in 2016 from IIT Guwahati under the guidance of Professor G. Krishnamurthy. To broaden his expertise, he undertook postdoctoral research as an institute postdoctoral fellow at IIT Madras, at CISR Center Leather Research Institute, and later at Hokkaido University, Japan, before joining WPI Nano LSI in 2025. His contributions to molecular photochemistry include pioneering work on proton transfer triggered dual emission systems, environment sensitive fluorescent probes for self-assembly studies, visible light switches, and most notably photoswitchable auxins for spatiotemporal protein degradation. Today, Dr. Saugata Sahu will present the innovative photo-switchable AID system which uses light to precisely control protein degradation and re-expression. Let us in Please join me in giving a warm round of applause to Dr. Sahu as he delivers his talk on photoswitchable auxins, spatiotemporal protein degradation for studying dynamic biological processes. Thank you.
Thank you for the kind introduction. And thank you for inviting me for this lecture. And I really thank to the organizing committee and also especially to Professor Ashok Kumar Mishra, who has been introduced me to CAOSA 2025. So I would like to share the PowerPoint presentation. So is it visible, this PowerPoint presentation, if you kindly confirm it?
It is visible. Saugata, go ahead.
Thank you. So,
Hello, it's visible, sir.
thank you. So today I like to talk about molecular photoswitch and its application towards the site-specific protein degradation. So I am Dr. Sogato. I am an assistant professor in Professor Mark McLachen and Professor Akine Joint Lab in WPI Nano LSI, Kanaja University. So this is the first before jumping to the research thing, I would like to mention this is the Japan and this is the location where, just a moment. Sorry. So this is the Kanazawa prefecture and where the Nano LSI is an institute inside Kanazawa University. And these two are my lab head, Professor Mark McLachen and Professor Sigihasa Akine. So today I'd like to talk two things. One is phenyl azothiazole as visible light switch, and the second one is a protein degradation with spatiotemporal resolution, an application of photoswitch. So first, what is a photoswitch? Photoswitches are the molecules that switches between two different states upon light radiation. So most common examples are the azo switches. Upon light radiation, it isomerizes from the E isomer to the G isomer. And other few photoswitches are like this dithiethylene. So this is two thiophene are linked to the one CC double bond. And upon light irradiation, it goes from the open structure to the closed structure. And another one group of photoswitch is the spiropyran merocyanine, which also shows the bond cleavage upon light radiation from colorless structure to a colored merocyanine structure. So among all these photoswitches, azobenzene are the most promising because this is, first of all, the ease of synthesis. Azobenzene can be synthesized in a much simpler methodology, and it is having large geometric and dipolar changes. From the E azobenzene, if you go to G azobenzene, it changes the structure from a planar structure to a bent structure. And another thing is the tunability of the thermal back isomerization. One molecule goes from E isomer to G isomer. And then, since this is a metastable state, it again return back to the E isomer. So now by chemical modification, we can tune the thermal back isomerization. And also we can do the spectral manipulation by push-pull design. And also this structure, adjuvant structure, is a very tiny structure, very much suitable for the receptor ligand interaction. So that is why among all other photo switches, these are the most promising one. And if I need to talk about the application, is the one of the application is as the molecular photo switch. These molecules can be utilized as the uh, stimuli responsive material. And at present, I am working on host guest type of stimuli responsive host guest material. So one example of stimuli responsive material. And also in photopharmacology, so let's consider the ligand is binding to the receptor, and that ligand, that binding is very much site specific. Let's say the E isomer is binding suitably with the receptor, and once with light we change the structure and dimension to the G isomer, then it will not bind anymore with the receptor or the protein, and the protein functionality can be controlled by just using light. And one of the most recent application of this azobenzene type of molecule is as the solar thermal fuel. So if you see in this diagram, there is upon irradiation, it reaches through the metastable state, which is actually the energized, more energized state. And if it is having a longer lifetime, this metastable state, if it is having a longer lifetime, then we can store that energy. And now, if the irradiation can be done with the solar light, then we can harness the energy from the solar energy with the system. So this is one of the most recent application of the molecular photo switch. But there is a limitation. The most of the edge of photo switches are UV light responsive. So that is, see, for the solar light, we know that around 490 to 500 is the most efficient intensity of the light. But means if it is absorbed in the UV light, so it will hardly effective material for the solar radio switch. On the other hand, for the bi application also, if it is UV radiation like this absorb around 320 nanometer, if it is a UV radiation, in that case also, it will means not good at all for the cell, and also other like cell penetration, those things are obviously is not good with the normal adjuvant gene. So that is the reason why researchers are trying to approach to the visible light switches. So one of the very promising way to reach the visible light switch is the this substitution at the ortho position. So earlier people reported that if the four ortho positions are substituted by the fluoride group or the methoxy group, then the band separation, that n pi star band. So before telling this one, I must talk about the pi pi star and n pi star band. So for this molecule, once it is in the most stable E isomer, this is the blue one is the pi pi star band, and this blue one, this is the n pi star band. Now once it is irradiated with light, then it goes to the isomer state. The G isomer is having the n pi star band around here and the pi pi star band around here. So the band separation, due to this significant band separation in the visible range, we can irradiate just here to achieve the G isomer and just here to achieve the E isomer. So this is one of the very significant work to achieve the visible light switch. But there is one limitation. If we need to use this molecule for the as a photo switchable molecule for any bioisoster, this is very bulky and hard to go inside some receptor or binding pocket. So there are other methodologies also there, like substituting with electron withdrawing group or electron donating group. In that case, also we can reach the visible light switch. And the most recent technique is the substituting one of the benzene ring with heteroaryl, or substituting both the benzene with the heteroaryl. Most recently, we developed, or we reported, phenyl azothiazole as visible light switch. Just substituting a thiazole unit in the benzene ring, we can we can make a visible light switch. This phenyl azothiazole, or we can, if we say PAT, phenyl azothiazole, these PAT molecules, it undergo bidirectional visible light switch. So we developed several different derivatives, and also uh, uh, we established that most of the derivatives are visible light switch, and this is the isomerization behavior of the that phenyl azothiazole. We can see that even 430 photostationary state also, it is almost 60 to 70%. And if we use 405, they are almost 80%, 80% conversion, E to G conversion happens. And if we use 470 nanometer light, then the visible light, then also G to E conversion happens. Also, if we just substituted a electron donating group at the para position of the phenyl ring NMe2, then we saw that rather than this wavelength maxima reaches to almost 470 or 470 to 480, and we can switch using 470 nanometer light for the forward and with the 627 to 625 nanometer PSS for the backward. But in this case, the backward reaction is much faster as compared to the means much faster as compared to the parent one. So we try to understand that what exactly happens here for the phenyl azothiazole and that 4-NN dimethyl amino substituted case. So both cases we found that there is a significant shift of the electron cloud from the terminal ring to the NN bond in the from HOMO to LUMO. If you see, from the terminal ring to the NN system, NN double bond, there is a significant electron transfer happens. So that is the reason why there is a shift towards from 323 in azobenzene to almost 365 in phenyl azothiazole system. So, well, we established that phenyl azothiazole and its derivatives elevate excellent bidirectional visible light isomerization. But we asked that whether the methodology we use, the reaction mechanism, is sufficient to introduce the phenyl azothiazole as the bioisoster. What I want to mean that if I need to make some biomolecule photoswitchable, then the methodology we used, or the reported methodology, can we establish a photoswitchable or thiazolyl photoswitch based bioisoster? So if you see that this is the reaction mechanism, that one we followed is really harsh and not at all suitable for the delicate bioligands. So then we look for different synthesis approaches. So one is the azocoupling. But for the azocoupling, obviously we can make the thiazolyl diazonium salt, but we must have a electron donating phenyl ring to couple and form the azocoupled product. And also we tried with the aryl lithium, thiazolyl lithium salt to make the phenyl azothiazole formation, but actually failed. And this is our report earlier, what in the previous slide I showed. We followed this ring closing mechanism, which is having really very low yield and followed a very harsh condition. And this is a very particular ring closing reaction for the azopyrazole system. So this molecule even had been reported and synthesized, this side one thiazole and this side azopyrazole, but very specific. And similar to the azocoupling, means only the electron donating unit only can react with the phenyl azothiazole diazoinium salt, phenyl diazoinium salt. Now, another one is the very promising for most of the azo dye synthesis, the Beer-Mills reaction. But if I need to get a nitrous derivative of this thiazolil or the vice versa way, it is bit difficult. But in our lab, we could achieve this phenyl azothiazole using the Beer-Mills reaction, but yield is very, very low in this case also, almost 10 to 20%. The another one very effective method is the Buchwald-Hartwig amination. We tried this one from a bromo derivative of thiazole, but we could not succeed in this case also. So most recently, we found a novel one-pot strategy to make the phenyl azothiazole. So in this case, what we did, just we took a one equivalent of phenyl PHNO2 and BF4 minus, one equivalent, and two equivalent of 2-trimethylsilyl thiazole. In this case, we found this benzene diazonium tetrafluoroborate salt very effectively react with 2 if I name it 2-TST, and it gives the phenyl azothiazole almost in 80% yield in dimethyl formamide just within 6 hours. So this reaction is one pot and very short reaction time, and it provides moderate to good yield and high substrate tolerance. So here are the reaction scope. We found that diazonium means the different diazonium salts like unsubstituted benzene, ortho-meta-para-substituted benzene, ortho-disubstituted benzene, and also heteroaryl, which is the most recent research topic, like both side heteroaryl based azo derivatives could be synthesized using this methodology. And this is the mechanistic aspect. I'll not talk in detail, but we found that we need 1:2 equivalent, like 1:1 equivalent of N2BF4, PH N2BF4, and 2 equivalent of thiazole. And also we found that the initially the cis product, the most least stable product, the G isomer is usually formed, and then it goes to the E isomer. And this is the within 60 minutes, the reaction is very much efficient. Within 60 minutes, almost reaction is almost completed for phenyl azothiazole system. And this is the proposed reaction mechanism. So, and oh, one more thing I'm missing, that we tried the reaction with thiophene derivative. So 2-trimethylsilyl thiophene, but in this case, the reaction did not go, which showed that the N, the sp2 nitrogen here is very important for the reaction. So, well, this is the photoisomerization behavior of different phenyl azothiazole derivative. And we just substituted, we focused on the ortho substitution, and we found that these molecules, this 2-methoxy substituted and 2-methoxy and 6-methyl substituted derivative, in this case, the E to G isomerization is almost quantitative, means with 405 nanometer light irradiation, almost 100% isomerization is possible. And they are very much fatigue resistant. And also for the bis heteroaryl substituent also, we achieve that the molecules are visible bidirectional visible light switch. And most interestingly, we can tune the property just by changing the moieties. Like if I talk about the thermal back isomerization, when it's converted into the G isomer, after that, this is T half is 2.4 hour, this one. And once this is disubstituted, we found that T half has been increased to 53.3 hour. On the other hand, for the bis heteroaryl system, these are significantly low. So we also try to perform a few theoretical calculation to found that why during the ortho substitution the T half increased, and we found that the transition state, this all the transition state structure, the is become more unstable, and that is why the del G dagger, the activation gives free energy, is increased. For example, this 7 is the dibromo substituted. So in this case, there is significant interaction between this bromo and this nitrogen, and this here is the strong van der Waals repulsion. And that is the reason if there is ortho substitution, in the transition state, there is a significant interaction, repulsive interaction, and which makes the molecule transition state more unstable, and the del G increased, and the half-life also increased for the G isomer or the cis isomer. So in this work, we have found a very efficient one-shot methodology for synthesizing visible light switchable phenyl azothiazole derivative with very moderate to good yield and with high substrate tolerance. So in my next topic, actually, I'll talk about the protein degradation with spatiotemporal resolution using photoswitch. So this is actually, we can be considered that one application of the photoswitch, how the photoswitchable molecules can be utilized to control the protein degradation within a cell. So here the objective of the work to achieve so first I should say that these all are the GFP, so green fluorescence protein, and the target is to degrade this green fluorescence protein only within a few cells, but not on the other cells, keeping the neighboring cells proteins intact. Since the light can be applied with very high precision way within a very micrometer region, so we can utilize the light and we can control the protein degradation. So I must talk a little background before. So that is this 5-phenyl indole acetic acid. This molecule has been reported for controlling the protein degradation. So earlier, I think, yeah, Professor Hosoi, she talked about the protein dimerization. So protein dimerization is the dimerizing of two different proteins. Let's consider this is one protein and this is one protein. And in this case, if we think that the dimerization is induced chemically, so if we add this one, the two protein will dimerize and subsequently protein degradation will occur. This is the target protein. But for protein degradation, first these two unit, this unit and this ethyl ligase should be dimerized. So this 5-phenyl indole acetic acid works as a molecular glue and cause this dimerization, and this ternary complex cause the protein degradation. Now we thought that if we can make a photoswitchable phenyl indole acetic acid, so this unit, if we just introduce a N double bond N, this unit is very much similar structure, having very much similar structure with the non-photoresponsive 5-phenyl indole acetic acid, and will behave in a similar manner, cause the protein degradation. On light irradiation, as I mentioned, that there will be a huge structural change, and this cannot go inside the binding pocket here, and the protein degradation will not occur. So this was the target, and we synthesized the molecule using the Buchwald-Hartwig methodology. And this is the photoswitching behavior. So these are highly fatigue resistance among, means we can switch multiple times between the photostationary state. And this is the G isomer. Once we irradiate with the 365 nanometer light, there is almost 95% conversion from the E isomer to the G isomer. Only 5% of E isomer does exist. So next we tried the molecule 1 for the conditional protein degradation. So I must clarify that these are the cell's nucleus, and GFP has been localized in the nucleus, and GFP has been expressed in the cell nucleus, and our target is with our molecule whether the protein degradation can occur or not. So we incubated these cells with our ligand 1 for 4 hours, and after 4 hours we saw the most of the GFP are degraded. So to confirm this one, we perform Western blot analysis. So Western blot analysis will confirm that no other factors but the EGFP has been degraded. So if you see that here, in presence of one 10 nanomolar of one, if you see that 10 just 10 nanomolar of ligand 1 can cause the EGFP degradation, but in presence of light there is almost no degradation occurs. You can see both here and here, both case. So to quantify this result, we use the flow cytometer technique, and with the flow cytometer technique we found that this is in the dark. It is very efficient. The EC50 value means the protein degradation. This is the maximum intensity of the protein, and this is the 50% of the protein. Degradation happens just with 1.26 nanomolar concentration of 1. Now, if we irradiate, then the EC50 value goes to almost 325-fold higher. So this is actually remarkable result, and it is we realize that this one we achieve because the molecule act as a E molecule, that the E isomer act as an agonist and the G isomer act as an antagonist. That is why we could achieve a 325 fold difference in the EC50 value. And after that we establish the temporal resolution. So with in dark, so we can, it causes the protein degradation, then again with light it goes up, then again dark, it can cause the protein degradation. So we can on and off, means with time we can, just with light, with triggering light we can control the protein degradation. And here is the most interesting thing, the spatial resolution that we have achieved. So we just irradiate the 365 nanometer light from the bottom, and you can see only this area there is no protein degradation, because the molecules are in the G isomer, which is inactive. But on the other hand, if we irradiate a green light, 520 nanometer light from the bottom, and another one light, guiding light from the top, the 365 nanometer light, then we can see that the reverse can also be achieved. So both we can achieve. So that is the thing. The key message is different gluing ability of the E and G isomer enables the photo switch to achieve conditional protein degradation with spatiotemporal resolution. So in summary, so we, in the first work, we showed the molecular design of a visible light switch and a very simple strategy to develop the visible light switch, and also how simple structure modification may be used to alter the photoisomerization behavior of phenylazothiazole. And in the later slide, I showed the how molecular photoswitches can be applied to control the intracellular protein degradation with spatiotemporal resolution. Thank you. Thank you for your kind attention.
So, thank you. Thank you, Dr. Savata. Any quick questions? So, Savata, looks like there is no questions.
Thank you. Thank you then.
Thank you very much for coming. Thanks. Okay then. Thank you very much.
Next, we would like to welcome Professor Digambara Patra from the Department of Chemistry, American University. Of research experience, he specializes in nanochemistry, fluorescence spectroscopy, optical sensing, and biophysical chemistry. His postdoctoral work includes fellowships in Switzerland, Germany, and Japan. Recognized among Stanford University's world's top 2% scientists, his honors include the Humboldt Fellowship, European Research Fellowship, JSPS Fellowship, and the Farooq Jabre Research Award. We now request Dr. Digambara Patra to present his talk on nanochemistry and optical spectroscopy, the next generation sensing applications.
Thank you very much for your kind introduction. Am I audible?
Yes, you are. This is Ashok Mishra
Yes.
here. Go ahead.
Yes, sir. Let me first thank you, the organizing committee, especially Stewart Science College, for taking this initiative along with Professor A.K. Mishra. Thank you, sir. Especially Mishra sir is very dear to me. He is my PhD supervisor. So it's my obligation and duty to be present here. Although I would like to be present personally, I could not make because of academic stuff. Today I have two lectures. I already had three lectures, one conference, and I have some other academic engagement in the evening. So I apologize for not being able to come and present it in person. I also thank the students, staff, and faculty who has really worked out to make this beautiful conference organizing at Kotak. So thank you again. So today I will be discussing some of our results based on um, nanochemistry and optical spectroscopy. So especially I will talk about fluorescence and resonance light scattering. And I will give a brief introduction about the molecule, although not all of my results is based on curcumin, but large part of this talk will be concentrated based on curcumin uh, chemistry. So curcumin, all of us know, it origins or it comes from the turmeric. Turmeric itself is very cultural in India. I don't call scientific because we use in food, we use in culture. I don't think any cultural events in India doesn't have somehow link with turmeric. Turmeric has this beautiful molecule, curcumin. Curcumin has been studied in lot nowadays for medicinal application. But today I will focus mostly on spectroscopic aspect of it, how we can use it for different kind of application. As I mentioned to you, I start my PhD with Dr. A.K. Mishra, and we started on synchronous fluorescence. Synchronous fluorescence, although was known in literature, maybe he first time explored this technique in India. So when I first started my research, independent research at American University of Beirut, I was just taking that experience from my PhD and try something. So this is what we found. We used curcumin fluorescence and then we applied synchronous fluorescence, and can we get some spectroscopic data from it? And this is something maybe Dr. Mishra or Professor Mishra would have already mentioned about synchronous fluorescence. I missed a lecture in the morning. You can see that in synchronous, we have contribution from both absorption spectroscopy as well as fluorescence or emission spectroscopy. So you have contribution from both, and technically we make that spectrum narrower so that it becomes better for analytical application. But here I applied for spectroscopic application like polarizability or ET30 or pi star, the solvent polarity. Can we correlate it with the synchronous fluorescence maximum? And we found something beautiful is about 15 or 16 years ago. So we found the relation with the ET30 synchronous fluorescence maximum when we take curcumin as a probe, and also we could compare with protic solvent like methanol, ethanol, water has different and we can also correlate with a pi-star scale. So thank you, sir. Especially this contribution comes from you. Basically, I can say that is the knowledge you gave to us. So then I focused on curcumin as a different aspect. How can we use curcumin as a green probe? Most of the fluorescence probe in the market are polycyclic aromatic hydrocarbon based. Some of them are quite known carcinogens like pyrene or anything, DPH, you can say. Many organic molecules we use in the lab are toxic. Some of them are really, we can say, cancerous or cause cancer. So when we talk about green chemistry, it is not only about you reduce the toxic chemicals in the day-to-day life, but also in the chemistry lab. So one of the approach I made is, why don't we use molecules which are well known, non-toxic molecules like curcumin as a probe molecule to investigate biological system or any physical chemistry method to know or to understand different kind of information. And secondly, also, there are many reducing agent in the literature. You can find most common one, sodium borohydride, which is a toxic. Good thing is it is not that stable. So sodium borohydride is more toxic than potassium cyanide, they say. So why don't we replace those chemicals with something which is we can handle it, and there is no side effects or there is no toxic effect. And curcumin works for that also. Some other plant extract or yeast can also work. So my approach was both use this molecule as a probe molecule for physical chemistry application and spectroscopy, as well as use that molecule as a reducing agent for preparing nanoparticles. So when we prepare metallic nanoparticles, especially, what is important is nanoparticles are not stable in the nano level unless we conjugate with something and stabilize it. Otherwise, they aggregate and form bulk materials like what we see, like gold or silver in day-to-day use. So the main thing is how we can control this size using different chemistry methods. So we can apply like polymorph, micelles, liposomes, proteins. There are different approach in the literature. You can use a macromolecules too. So we apply different methods and we stabilize different nanoparticles based on silver, copper, and gold nanoparticles. So one of the first approach in this was to use curcumin to prepare gold nanorods. So here we use some micellar chemistry. We use different kind of micelle like CTAB and citrate. So here, by controlling the CTAB and curcumin at a given particular condition, we can change the shape of the gold nanoparticles from the spherical shape to long nanorods. I will talk about the application of spectroscopy later on. Then we modified this one. The previous method had seed-based method, so we modified and wanted to make in one pot synthesis. In single pot, why can't we synthesize gold nanoparticle directly without using seed? And our target was to prepare nanorods. But interestingly, we changed different conditions, pH, temperature, and concentration, of course. And at particular concentration and particular temperature at pH higher than 13, we could able to get nanowires, which are longer than nanorods. And we investigate the mechanism. Maybe today I will not discuss about that. And we figure it out. The nanoparticles, actually, they grow only one of the side. They have many faces, like 111, 110, and other faces. But what we speculate or our data suggests that the growth occurs largely in 110 phase. And this is how they produce the nanorods and nanowires. Finally, they become nanowires at very higher OH minus concentration or hydroxy ion concentration. So why I was interested in nanowires, the main thing is I want to explore something called resonance Rayleigh scattering. Rayleigh scattering, all of us know, this is a scattering when you excite a particle at a given wavelength, the scatter coming out at that wavelength is called Rayleigh scattering. Especially the light interacts with the matter without doing anything. I can just scatter. And Rayleigh scattering occurs when the particle is much smaller than wavelength of the light, like dispersion occurs or interference we see, and what we say like rainbow, the wavelength of the incident light and the distance between the particles should match. Here the particle is smaller and we have a wavelength of light, then we see scattering, and this scattering is inversely proportional to the wavelength, 10 to the power 4 you can say. But normally this signal is weak. But when we do the same scattering at the absorption band or emission band, then this weak signal is enhanced, very similar to, we can say, resonance Raman. And this signal enhancement may not have many, day to day, like when we are exploring the information regarding the structural information of the molecule, but it can be very much useful for analytical application or sensing development. So because it can be highly sensitive for molecular aggregation, size, environment, concentration. So we can get many different information. Sometimes if the molecule is not fluorescence, we can still get the resonance Rayleigh scattering. So this is the aim. So we wanted to have a strong signal for sensing application. And now I went back to my nanochemistry, and there we prepare, as I mentioned to you, at different temperature and different pH condition, and we prepare nanowires and nanoparticles and nanorods too, and we compare the resonance Raman scattering. When we compare resonance Raman scattering of nanowires is much higher than that of nanoparticles. One of the reasons is these nanowires are not only they are longer in the length, although they are thin. I call nanowires because they are more than 1 micrometer in length. They have rough surface. So it is not about the size and shape, but the structure, the shape, the rough surface also enhance the scattering. Perhaps this is why we get much higher signal of resonance Rayleigh scattering for nanowires compared to nanoparticles. Then we use it for applications. So then we went to study the vitamin E or alpha tocopherol, and we could able to sense it, as you can see, very low concentration in micromolar concentration range. And we also found this method is quite selective compared to ascorbic acid and other vitamins. So ascorbic acid and vitamin C. So, and the sensing scheme is quite stable in the measurement time. Up to 1 hour we measure in the presence of, because this is resonance Rayleigh scattering. So there is no way there will be photo bleaching, because here we have only nanowire, so there is no fluorescent molecule attached to it. So then we were quite excited. Then we said, why don't we modify the ligand in the nanoparticles and change the approach? Because the ligand itself, or what the stabilizing agent, what you call, when we modify it, then we can change the chemistry, then we can target different analytes. So now our next goal was how to develop a method for glucose estimation. For diabetes people, they control glucose. So here we modify the nanoparticle, but we did not go for nanorods or nanowires. We went for spherical small or nanoparticles, and we modify with F108, the polymer. Then we target for glucose. And we found exactly what we wanted, the signal increase. Then we could able to sense glucose. One of the reasons why glucose makes this signal increase is the glucose helps to come to gold nanoparticle come together through the ligand. So glucose has many oxygen and hydrogen, so they make hydrogen bond pairs with the our polymers. Then this polymer brings the two gold nanoparticle very close to each other, and then the scattering increases. So this was the comparison, fructose, galactose, it works, but Other one, it doesn't work like acetophenone and other selectivity. So in general, for sugar, this method works. Then we further change this one to a different method. Instead of gold, now we focus on copper. So copper oxide, we prepare, again, I am not discussing about the synthetic method. So curcumin and then copper chloride, then we use it for preparation of copper oxide nanoparticle. I cannot say it is copper oxide or copper because exactly is almost same, and we did not have technique to actually explore whether it is copper or copper oxide, so we can say any one of them. So then we attach another polymer on the surface, and we could able to determine mercury in water. So again, here mercury binds to both this ligand, and then it increases the aggregation process. Then we were quite excited. So what about cysteine? Cysteine is quite important for the biological application, especially biomedical application, cystinuria determination. So we may measure here, we prepare copper oxide nanoparticle conjugating with cysteine, as you say, double bond S. Then we develop a analytical tool where we use ascorbic acid cysteine, which breaks it down. Then it reacts with your copper oxide nanoparticle, and when we monitor the resonance Rayleigh scattering. So basically, this is how the scheme works. The cysteine bond, so that brings all the copper oxide together. They form an aggregation, and this aggregation enhance the resonance Rayleigh scattering. So similar way, we also approach for persulfate. What about anion? We tested for cation. So then we target a different polymer just for specifically for persulfate, because persulfate is nowadays used for degradation of toxic compounds in the water, but its determination sometimes it may cause skin irritation and other kind of health issue. So their estimation is also important. So we develop a method based on resonance Rayleigh scattering for persulfate. So then what about other kind of nanoparticle? Then our focus was, instead of going more expensive one like silver or copper or gold, why don't we go for our sand, silica itself? So we develop a method here. We did not use curcumin, it's the plain silica. So small nanoparticle, silica nanoparticle, we prepare in the lab, as you can see. And what about the resonance Rayleigh scattering of this one? Can we get it? And actually we get some resonance Rayleigh scattering for silica nanoparticles. And then we try different ion. Mainly our focus was silver ion. Silver is now widely used for many applications, including solar cell application also. So silver ion determination is becoming quite important. So we tested it for silver ion determination, and we could get this method based on silicon nanoparticle, and we found really good result compared to the literature. You can see the interference in our method, and we can go up to 5 to 300 micromolar, so which is a quite wide range for the determination of silver ion. Then we focus on fluorescence part now. Now, this part was mostly resonance Rayleigh scattering. Then what about we take a fluorescent molecule, modify with nanochemistry, and prepare a new kind of nano capsule, we can say, and this capsule can increase the selectivity or sensitivity. So what we did, we used initially this kind of polymer, polyadenine sulfoxide. One of my colleagues, he was preparing this, so I just borrowed from him, and then we use it, and we prepare this poly A along with silica nanoparticles. So we form this kind of capsule, as you can see it here. So in the right hand side, and these nanocapsules has curcumin. We add curcumin, so curcumin is encapsulated inside the nanocapsule. And now we compare the fluorescence of this nanocapsule and compare with curcumin, and we measure different nucleobases like adenine, guanine, cytosine, thymine, uracil. And what we found, this nanocapsule selectively measures guanine, and the sensitivity also improves. We were very excited. This was the first publication in this area. Then we went to another polymer, which is cytosine oligosaccharide. We use slightly different method for preparing the nanoparticles. So we use a surface on the silica nanoparticle surface, simple adsorption, just to put the polyelectrolyte, in this case cytosine oligosaccharide. It will self-assemble and form this kind of capsule. What will happen then? The fluorescence changes, as you can see, although the intensity is quite low compared to the pure curcumin. But when we add different analyte, our target here was cholesterol, the signal remarkably improves. So the intensity goes very high. We were quite excited, and then we compare with curcumin. Curcumin also binds with cholesterol. Then we explore the different possibility. So what we found, when we prepare the nanocapsule, curcumin not only binds to cholesterol, but also binds to bovine serum albumin, human serum albumin, and it also binds to some of the like oleic acid. So many not hydrophobic molecule that binds with curcumin changes the fluorescence signal of curcumin, like as you can see here. However, when we prepare the nanocapsule, our selectivity completely switches. So this nanocapsule has no preference for BSA or oleic acid. It is selectively binds to cholesterol. And not only that, you can see the signal is much, much higher. Curcumin also binds to mercury and copper, because curcumin has this diketo group, and the diketo group binds to the mercury copper. And look at our nanocapsule, it doesn't bind. So completely we change the analytical application, the selectivity changes, so in the favor of the nanocapsule. So then we also went through the other kind of nanocapsule. Here we prepare PLGA, PDDA based nanocapsules, and we study some photochemistry. Like here you have the keto form and enol form, and you have deprotonated form of curcumin. And this is the absorption of deprotonated form of curcumin. This is the enolic form of curcumin. And when we prepare this kind of capsule, we can see these capsules are more hydrophobic, so the emission shifted to the lower wavelength. And then we use this method for this nanocapsule for the determination of the dopamine. Dopamine is mostly for mental health. The total dopamine concentration is estimated. So in biomedical application, and we could figure it out. As you can see it, compared to others, we got a very good selectivity for dopamine compared to other amino acids and other biological acids. So then we went through other kind of application, like again, we went back to the preparing gold nanoparticle, and what about we attach a supramolecule like curcumin here in a given distance. Our goal is we put a macromolecule like here, and then we add a fluorescence probe like rhodamine or acridine orange, and monitor the fluorescence, because we thought from rhodamine there will be energy transfer threat, posterior resonance energy transfer to the gold nanoparticle, and fluorescence will be quenched. And then the analyte, when it comes and have a competitive binding with this macromolecule, then it will kick out the fluorescence probe. Then the fluorescence will be dequenched, means it will enhance, and we can estimate for that particular molecule. So the idea was good and it worked. So in this case, we use rhodamine and our target was ATP. Selective estimation of ATP is very challenging. People use optamos for that. So we want to have a simple method. But one thing the reviewer commented, we should not say it threat fluorescence or posterior resonance energy transfer, rather because of the gold nanoparticle and distance are big little larger, he said surface energy transfer. Then we learned something new from the reviewer's comment, and then we could able to selectively estimate ATP. As you can see, UTP, GTP, all of them, they do not have any selectivity for this. So our method was quite easy and easy to do in the lab also. So we would similar idea, and we use copper oxide in this case, and we use because we want different now target. Our target was ATP here, so we use curcumin uril 7. We use 6, and this time again we go back to the dopamine idea, and we use dopamine, and we could easily recover the fluorescence in the presence of dopamine, and we got the um, uh, estimation for dopamine. So I will also focus slightly photochemistry part. So we prepared this kind of nanocapsules where we have polyalyl polyalylamine hydrochloride, and we use phosphate buffer and prepare this kind of nanocapsule along with curcumin. So curcumin encapsulated one. And based on the salt concentration, we can control the size of the nanocapsule. Our target was, can we understand some photochemistry based on the size of this nanocapsule? And this is the state fluorescence image. And what we can found is, this is very interesting. Curcumin fluorescence comes from excited state hydrogen or proton transfer. So the emission we get is after proton is gone from the enol form. So what we could find, we can really control this based on the size of the nanocapsule. So from the enolic form, when we have excited hydrogen transfer, intramolecular hydrogen transfer, then we can reverse the process, or we can encourage the process based on the size of the nanocapsule. We also use for monitoring the polarizability inside the nanocapsule. Like in this case, we use for silica nanoparticles, and we can use fluorescence as a probe molecule to understand the polarizability inside the nanocapsules. And recently we work on MOFs, and again, whenever we do for, like here, the application was biological application for drug delivery, especially curcumin delivery. We found a good result when it comes to the antioxidant activity. But as a spectroscopist, always we have a soft corner. So whenever I do such thing, I do some fluorescence and UV, and we found again in such molecules what kind of pore we have, which kind of environment we have. So we explore this one for aluminum-based MOFs and magnesium-based metal organic frameworks. And recently, we are also working on peroxide, how to stabilize it. These are being used for solar cell application, but they are very unstable in normal condition, especially in the presence of water. So we are doping with different methods like CTAP, cetyl, pyridinium chloride, and bromide. Recently, we published some of them. This is without CTAP, with CTAP, and stability dramatically improves, and fluorescence also improves. So again, the same one, when we dope with silica nanoparticles and we dope with CTAP, how the fluorescence quantum will, as well as stability of this kind of peroxide improves. So I would like to thank my collaborator and my team. And today I talk about my students, Mai, Rasha, Maida, Justine, Hanin, and Riham. And although I didn't talk about any of my collaborative work today, I also like to thank my collaborator, and thank you all for your kind attention. Thank you very much. This is our campus, how it looks.
Any questions, queries? So looks like there is no questions, Professor Patra.
Thank you, sir.
So thanks a lot. Thank you for participating. Thank you.
Up next, we have the pleasure of welcoming Dr. Ganesh Chandra Naik, Associate Professor of Chemistry and Chemical Biology at IIT ISM Dhanbad. Dr. Naik is a distinguished researcher and a leading expert in polymer chemistry and sustainable energy technologies. He completed his MSc from Utkal University in 2006, followed by an MTech in 2008 and a PhD from IIT Kharagpur in 2012. Over the years, his pioneering work has spanned energy storage devices, microwave absorption, and advanced nanomaterials with more than 100 impactful publications to his credit. He has successfully guided several PhD scholars and led prestigious projects supported by DST-SERB, DRDO, IUSSTF, and Sutra, making significant contributions to graphene-based nanocomposites, MXene hybrids, and a sustainable energy storage system. With great pride, let us welcome the eminent scientist. Please join me in giving a big round of applause to Dr. Naik as he presents his talk on surface chemistry insights from XPS for next generation storage technologies. Thank you.
Hello. Hello. Am I audible? Hello. 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 Am I audible? Hello.
You are audible, Professor Naik, but we are not able to see you.
Okay. Just
You
a
have to
second.
say something.
Is it now visible?
Right. Please go ahead. Thank you.
Okay. Okay. Sorry for disturbance. Okay. Thank you very much for the nice introduction, and I deeply apologize that I'm still in the Bhubaneswar, but I could not able to visit there due to some unavoidable circumstances. Having little bit of health issues right now. I just visited, traveled from Dhanbad to here, and I'll be next time. I'll definitely visit over there. Okay, thank you. And I was listening to the lot of lectures, and they are very informative and very focused on very advanced research over there. And by my topic, I'll be more concentrated on. I thought it will be a little bit of for the students, like whatever we are doing with XPS in our lab, some of the problems what we are facing, how to overcome that. It includes one case study and one introduction to this XPS, and then the final points that what needs to be done and what not during this energy research over there. So let us start this one. I'll just start with a case study of that Samsung one, and before that one, I'll just tell you that what we did, what we are doing in our lab. Basically, our lab is focused on development of the supercapacitors, and we are also working on the sodium-ion batteries along with the micro absorption materials. And right now, we are also focused on how to convert a waste to the energies, and mostly we are working on how to utilize a waste waters which are very containing a lot of heavy metals like chromium, cadmium, arsenic, and lead that we are removing. And up to that point, all environmental chemists they did it. But what we are doing new is we are just utilizing those separated metal ions for development of batteries as well as the supercapacitors over there. This is our team, and we are actually 5 GRFs are there, and one PDF is working on these projects, whatever we are doing over there. And let's come to that particular case study, which is a very interesting one, and that gives us a lot of information that why we are working on these particular systems. Okay. And this is a well-known study of that Samsung Note 7. We already know that what happened to this Samsung Note 7 over there, and there is a lot of explosion occurs in those batteries of Note 7, and due to that one, the share of the Samsung has drastically reduced. That we already know. And they did a thorough analysis of what goes wrong with their system. because they are having a very stable system, and but they are not able to identify what happened over there. So they published a report that what is going on in their batteries and why they are exploding. So basically, it contains lithium-ion batteries, and as of all batteries, it also contains some cathode, anode, and separator and electrolyte. And the problem is the electrolyte, which is a very flammable one, as well as the separator, what they are used over there. They have reduced the thickness of those separator to a greater extent to increase that energy efficiency over there. So in a term, they have compromised on the safety of those particular batteries. And what happened over there is they have find out there are some abnormal features in their batteries which is present in the Note 7. In normal cases over there, just a second, I'll just normal cases, this is basically a wrapped up cell, and it is having a multiple cathodes or anode over there, and somewhere they have find out they are basically wrapped up and they are touching with each other over there. In some batteries, they find out that anode part over there, the negative electrode over there, they should be placed at this normalized placed over here. This is the normal case. But they find out the end point, it is basically in the bending structure, and that's why it is under a lot of stress, and that's why there is a possibility of failure as well as the short circuit over there, and which leads to that particular flame in that Samsung Note 7 batteries. And the last and a critical part, what they find out that during this tabbing or this welding of those particular batteries, they find out this cathode over there or anode, they are pressed a little bit more, so that this separator which is there, they are basically pierced out or that has been broken, and that's why the cathode and anode, they are coming in contact with each other. That's why there is a spark is occur, and the electrolyte is very flammable, and that's why the fire has started over there. So these are the major problems which is associated with that Samsung Note 7, which trigger the flame in those particular batteries. But apart from this mechanical failure, there is one more thing in the batteries which is very critical, which is basically your lithium dendrite formation. Whenever you are getting these batteries, there is a dendrite formation is always occurs. And the people are now working out how to reduce that particular dendrite. And if you are using a very thin separator and the dendrite formation is very rapid, there is a greater chance that dendrite, it can break down those separator, and there will be a contact between a cathode and anode. And once they will in contact, since the energy density is very high, there will be a spark. Once there will be a spark, the electrolyte will going to catch fire. If there is going to catch fire, then the whole system may explode over there. So that is the major problem. And that's why people are now working that how to create a stable cathode and anode systems over there. And there are various type of cathode and anodes are now being developed for lithium-ion batteries as well as now sodium-ion batteries and other type of batteries. The major thing is all those batteries are involved in oxidation and reduction reaction over there. If you are having an oxidation reduction reaction, then it involves electron flow. If there is an electron flow, there is a chance of change in oxidation states during this charging discharging cycles. And if this, after the charging and discharging cycle, that material, it will not come back to its original oxidation state, then the batteries start to degrade. And that is the reason that why our batteries are not working forever. There is having a depletion in that battery capacity after a certain time. And if you can track that one, that how this particular degradation occur or how this oxidation reduction reactions are changing the primary oxidation states of those particular materials, then you are having a tool to identify what needs to be done to that battery so that the lifetime it will increase. So there are various X-ray techniques now being used. Apart from this X-ray technique, there is a microscopic techniques and various material chemist techniques are there using. But my interest will be that this XPS over here, that how this XPS, it is going to help you to identify that how these batteries are become more stable or not. Okay. So if you go to this particular XPS, this is well known, and this is for the student if they are still not aware of this particular XPS. We know that you are having a sample, it contains a lot of atoms, the X-ray is hitting this particular atoms, and the core orbital electron is knocked out. Okay, and this core orbital electrons energy, kinetic energy, depends on the incident energy and the binding energy of this electron toward this particular nucleus. Basically, the kinetic energy, it will be what is the energy we are giving to that system minus the binding energy and minus the phi value, which is needs to be calibrated so that it will overcome the pulling force between the nucleus and the electron over there. Okay, and if we track the kinetic energy of this particular electron, we can able to know the various oxidation state of that particular element present in that particular sample. Okay. Now, if the oxidation state is going to change, then the binding energy of that electron, it is also going to change. If the binding energy changes, then we can able to track that binding energy by measuring the kinetic energy of this particular electron over here, and that way we can able to track the change in oxidation state. And based on that one, this XPS has been developed over there. And now we are going to look into that major part, what we are more interested in, that what are the common challenges to XPS analysis in this particular energy research over there. Okay. So the first thing is the preparation of the sample. Whenever we are giving our samples to our student to go for XPS analysis, they simply submit that particular sample to the operator and they will come back. Okay, so they are not bothered about how they are preparing the samples and what conditions under which they are doing that analysis. Due to that one, I have faced a severe problem that we got a multiple wrong results and we have to repeat those sample multiple times to get the accurate nature of that particular sample over there. Okay. And what are the major sample preparation techniques required for this lithium ion batteries? Basically, the lithium surface contamination is a major thing, that if you are working on this lithium ion batteries, you have to make a half cell. And for that half cell, you have to use a lithium metal over there. And whenever you are having a lithium metal, you either you open it inside a glove box and you are thinking that particular surface is very clean, but irrespective of whether you are opening inside a glove box or in a vacuum chamber, you will always find some of the hydroxide as well as some of the oxide present on that particular sample or on that particular surface. And basically, when you will take this particular lithium and you are making a half cell and then you will test them, this oxide layers or the hydroxide layer is basically affecting the electrolyte and electrode interface reaction over there. And that is something we have to be very careful about. And to overcome this particular problem, what we did is, whenever we are using this particular lithium metal, we know we are going to put it into an electrolyte. So what we are doing, we are just dipping our lithium metal inside those electrolyte solution, and then we are cutting that with a knife. So what happened over here is, when you are cutting that lithium metal, a fresh layer or a fresh surface, it will be formed, but that fresh layer, it will be directly in contact with the electrolyte. So there will be no changes in the oxidation state or the nature of the lithium metal when you are going to make it into a coin cell for your analysis over there. And that basically, we are getting a better result when you dip it and cut it, rather than cut it and then you put it into the coin cell and you add your electrolyte inside a glove box. So this is one thing you should be very careful about. And when you will take to confirm this one, that whether this lithium has already been having an oxide layer or not, we have analyzed both lithiums when it is dipped and cut, or cut and then we are going to fabricate this particular coin cell over there, and we find out a very drastic change in that particular oxide contamination onto this lithium metal surface when it is cut inside a electrolyte solution over there. The environmental restriction is one of the more problem we have faced, that our XPS is not inside a glove box. So at a certain point of time, we have to open it and then you have to put into this particular XPS instrument over there, until unless you are doing a in situ XPS analysis over there. So this environmental things, whenever we are putting inside if you are not having that facility, that glove box, or you are not having a XPS in your particular department over there, there is a greater chance of surface contamination due to this environmental exposure to that particular lithium metal over there. So this needs to be overcome over there, then only you will get a accurate oxidation state of those particular materials. This is sample surface roughness is one more thing, and this is the peculiar thing we got, that when you are using a knife, I told you that we are going to cut that particular lithium metal with our knife, and we have find out that if that particular knife, that edge, if it is having a little bit of blunt structure, the surface is basically became very rough over there, and then we got a different properties over there. We have tested this one multiple times with multiple knives, and we find out that one, the surface roughness is actually changing over there, and that particular roughness is basically affecting the electrode electrolyte interface area over there, and that is also affecting our properties. And this is also very critical when we are analyzing our non-conducting sample, when you are doing a post-mortem analysis. When you are doing the post-mortem analysis, we are forced upon those coin cell over there, and if that particular coin cell electrode is basically bent, then we find out there is a lot of defects or the surface breakage is been occurred over there, and that way we find out there is a shifting in that particular XPS peaks in those areas wherever the surface roughness is more as compared to the other areas over there. The sample nature, this is one is also related to that particular non-conducting sample. Most of the cases we are using this metal oxide or metal based cathodes or for our battery system over there, and which are mostly are non-conducting in nature. And we are having, these are also very powder in nature. So how we are doing it, we are either stick it into the carbon tape or we are making a pellet out of that one. And we have find out when you are making a pellet, the nature of that particular XPS is a little bit different as compared to when you stick it onto that particular carbon tape directly. And then when we are doing this coating to make this a conducting surface, we got a very different results over there. And basically for each sample, we need to be calibrated that particular coating time and the coating area over there. Okay, so then only we got a very good result and a repeatable result over there. So this is something we have to look into. And then the analysis and the collection of the data, this is one more thing, that selection of the source. We have, this is a very known thing that we are generally using aluminum or magnesium alpha for our this XPS analysis over there. But we have sent our sample for a high energy radiation with either chromium or other sources over there. We got a much better resolution over there. So my suggestion will be to the students who are working on these systems, they should explore the other sources, then only they will get a high resolution XPS images over there. Charge neutralization is one more thing we have to look at, because for the non-conducting sample, this is inevitable. We have to do the charge neutralization. And in lithium ion batteries, whenever we are using this particular cathode system, we have find out there is a minute shifting in those particular peaks, and that needs to be a proper charge neutralization with calibration so that you can get a better properties and the repeatable result over there. And this calibration is one more and the most important thing. We have find out that XPS, whenever we are using for very multiple times, there is a shifting in those peaks. So that XPS needs to be calibrated before we are going for that particular analysis over there. So these are the some of the problems we have faced in our lab during this energy material analysis with this particular XPS. So I'll just show you few of our analysis, and with that one, we can able to conclude that what we are doing in our labs. This is particularly a plot for your NMC cathode material, what we have used over there. Okay, and in this case, we have got a multiple results or multiple peaks over there. Okay, and this is typically a reference plot over here, and we can get multiple nickel peaks over here for the 2s, and this is for your auger electron, and this is for your nickel 3s and 3p over there. Okay, and this plot, it is showing that one, what are the elements present in our survey spectrum over here. This is one work we did in our lab where the waste to energy concept we have applied, where we have used arsenic contaminated water over here, and we have used walnut shells and to make those porous carbon, and this porous carbon has been deposited with this alpha Fe2O3 so that the arsenic it will be adsorbed over here. Once the arsenic it will be adsorbed over here, we have heat treated this whole arsenic containing this porous carbon to make a electrode for our supercapacitor device over here, where this arsenic containing compound we have taken as an electrode and the porous carbon is another electrode we have taken, and then based on that one we have fabricated a device and to demonstrate the device is basically working over here. Now the thing is, whenever we are absorbing this particular arsenic, the problem that arsenic may also leach out during the use of this particular battery system or this particular energy storage devices is there. So for our need, this arsenic needs to be chemically bonded to our system so that the arsenic it will not leach out, because our objective is to produce a clean water so that the arsenic free water over there. If we are absorbing arsenic from that particular water and during our use, if the arsenic will go into that system, then our purpose is not solved. So that's why we have checked that formation of any bond between this arsenic and the iron over here, and through the XPS we have find out there is actually a iron, arsenic and oxygen bond is forming over here, and that way this particular arsenic now it is in the -3 oxygen state, and that way we have stabilized this arsenic, and XPS give us a tool that whether it has been stabilized over there or not. In this one we have used to synthesize magazine, because this is basically a new material now people are working on. This is a magazine and it based on the titanium, aluminum and carbon over there, and aluminum is basically linking between this titanium carbide sheets over there. So somehow if I remove this particular aluminum layer, the titanium carbide sheets it will be separated, and this will be have a two-dimensional sheet which are very conducting in nature, and this will have a conductivity similar to the graphene, and it can be used for the energy storage devices. Now for the synthesis of this particular magazine, people are using take the max page and then put it into that hydrogen HF over there, and the HF it is going to east out the aluminum from the intergallery, and then you are going to get those particular magazine sheets over there. But the problem is this etching it takes around 72 hours to complete over there. So we have tried to remove that particular aluminum layer within a shorter time by using a electrochemical method, and by applying a potential within this particular HF layers or HF electrolyte over here, and I am putting this particular max phase within this particular electrolytes. We have find out that one that the aluminum leaching has done preferentially, and after 120 minutes over there, after only 2 minutes, we are able to synthesize this particular magazine sheets, and these are the etching layer. These cracks what you can see, these are the magazine layers where the aluminum has been etched out from that particular system. So to confirm this one, we have did this particular XRD, and we have find out that one there is a significant change in the despacing when we are removing this particular aluminum layers from this particular systems. And then we have used this XPS to find out whether the aluminum layers or aluminum content has reduced or not. So when before that particular analysis, when you are doing it for only 20 minutes, the aluminum content is about 4.9% over here. And when you are doing up to 120 minutes, we have find out the aluminum content is reduced to 0.1% over here. That means there is a drastic reduction in the aluminum content, and XPS help us to identify that one. Apart from that one, the major problem is if you continue this particular etching for a very longer time, there is a possibility of titanium dioxide formation and the whole structure may break down. We have find out that one there is certain formation of the titanium dioxide in fact, but the content of this particular titanium dioxide is much lesser as compared to the other system what they are using for the rapid synthesis of magazine over there. So these are the magazine sheet what we have synthesized over here, and with that one we have fabricated a device, and with that device we have shown that one it is able to produce a working energy storage devices over there. We have compared our result with the other reported results, and we find out that our results is much similar to them within compared to this particular results. Our results is much compared to them, and that's why this process is also a very viable process to bulk cell synthesis of this particular magazine sheets over here. And we have also calculated the cyclic stability of this particular systems, and we have, after the 10,000 cycles, we have find out there is a 80% retention in the specific capacity of these systems as compared to other properties what we have studied. In this 27 and 28, we have find out it has been reduced to 60% over there, and 29 and 30 they have reduced up to 45% over there. So we got a higher cyclic stability, as well as the time of synthesis has been reduced drastically. So these are the few of the words, and I will going to conclude with my lecture on this, that the sample preparation for the student, they should be very careful about. And when you are preparing that XPS sample, you should be very careful whether it is a conducting, non-conducting, whether it needs charge neutralization or not, or whether the thickness of the sample or the roughness of the sample is uniform or not. Okay. So with this one, I'm going to conclude these things. Thank you.
To welcome Dr. Katarzyna Jęczak from the Department of Biomolecular Medical University of Lodz, Poland. Her research focuses on developing new analgesics from endogenous opioid peptides and studying the anti-cancer activity of synthetic heterocyclic compounds. She has completed international research internships in Belgium and Sweden and a postdoctoral fellowship in France. Recipient of the Minister of Health Team Award, the L'Oreal for Women in Science postdoctoral scholarship, and other prestigious honors, she has led multiple funded projects including Polpharma and NCN. With great respect, we invite Dr. Jęczak as she presents her talk on characterization of pharmacological activity of novel opioid peptide.
Good afternoon, ladies and gentlemen. I will try to show you my screen, so just give me a minute. Can you see my screen?
Yes, yes, we can. Please go ahead.
Thank you very much. So, good morning, good afternoon once again. I think that I will turn, maybe not yet. I would like to thank the organizers of this meeting for the invitation and for giving me the opportunity to present the part of our results. I think that I will turn off my camera because my connection is not so good. Okay. So today the topic of my presentation is as follows. So characterization of pharmacological activity of novel peptide analogs as a potential analgesic drugs with reduced side effects. Okay. Pain has always accompanied men, and people from centuries have sought pain relief remedies. Opium is a dry poppy seed juice, and it was the first painkiller known in ancient times. Morphine is the most important ingredient of opium and was isolated from poppy seeds in 1803 by Sir Turner. Its structure, which is alkaloid structure, was elucidated 120 years later. And of course, to this day, morphine is one of the most powerful painkillers used in medicine, especially to combat severe pain like in cancer. When we administered morphine to the patient, we obtained the analgesic effect, but also some severe side effects like excitation, euphoria, tolerance, physical dependence, respiratory depression, and inhibition of gastrointestinal function. So patients suffer from constipation. Opioid receptors, now a few words about opioid receptors. So in 1954, it was concluded that analgesic action of morphine is mediated by opioid receptors, which are localized in human and other in brain. In 1973-97, three types of opioid receptors, so Mi, delta, kappa, or More, Dor, Core, respectively, were described, and their endogenous ligands were isolated. However, the presence of opioid receptors and their ligands was reported not only in the central nervous system, so here we have a brain and spinal cord, but also in peripheral tissue, for example, in stomach, intestine, blood vessels, and in various cancer cell types. Opioid receptors belong to G protein coupled receptors family, and are coupled with GI proteins. So activation of these receptors results in inhibition of adenyl cyclase activity and reduced formation of cyclic AMP, activation of MAP kinesis pathway, opening potassium channels, and closing of calcium channels. And why it's so important? Because all these coordinated actions result in intracellular hyperpolarization of neurons. And finally, we can observe pain reduction. So this is the inhibition of pain signaling. Although all three types of opioid receptors are involved in analgesic process, the activation of each type of receptor produces different specific effects. So, Mi opioid receptor most strongly involved in transmission of analgesia, but also of related side effects. Delta transmits analgesic effect less effectively, but also causes fewer side effects, while kappa transmits analgesic effects mainly in peripheral tissue, but is also responsible for strong dysphoric effects. And the discovery of opioid receptors resulted in search for their endogenous ligands, and in 70s, some delta selective enkephalins later kappa selective endorphins and unselective endorphins were discovered. And this peptides we call all this we call opioid peptides. Later on, in 1997, Zadina and collaborators isolated from the mammalian brain four amino acid peptides, which had very strong mu-opioid receptor affinity and selectivity. Here you can see this is the mu-opioid receptor affinity, so it's in sub-nanomolar range and very good selectivity. And since these two peptides work through the same receptor as morphine, they were called endomorphines. So here we have endomorphin 1 and endomorphin 2. Other opioid peptides were isolated not only from the mammalian brain, but for example, from the body fluids, from milk, from blood. And here you have an example. This is morphicaptin. This is also amino acid peptide with high affinity to mu-opioid receptor, which is isolated from enzymatic digestion of milk protein. This is important peptide for me because I perform a lot of studies on analogs of the peptides during my PhD studies. And pharmacophore groups of opioid peptides. They are important for binding to the receptors. So we have hydroxyl and amino group in the first amino acid in tyrosine. We have aromatic ring in amino acid in the third position. They are important for binding to the receptor. Here we have proline, which is some kind of linker, and it's very important also because it keeps amino acid in the first and third position in the right distance. And it's important for binding to the receptor. And the discovery of opioid receptors and isolation of their endogenous ligands open the new possibilities for developing of novel peptides with improved pharmacological profile. So people started to search for peptides which will have a strong antinociceptive analgesic activity, but will be deprived the side effects of morphine. And peptides generally are characterized by high activity, high selectivity, and low toxicity. However, native opioid peptides have several limitations. So here you can see the limitations. So this is low metabolic stability. They are easily degraded by proteolytic enzymes. So it's difficult to administrate them orally. So other routes of administration must be introduced, like intravenous, subcutaneous, and so on. Poor bioavailability or oral activity, low blood-brain barrier permeability. So they do not cross the blood-brain barrier or cross, but in a very low way. So they cannot reach the place of working. So the place where we have opioid receptors. So to overcome these problems, various strategies are proposed. So we can do many chemical modifications, what we do in our lab. So this is incorporation of unnatural amino acid and the amino acid, forming of non-peptide bonds, cyclizing linear structure, and synthesizing conjugates and hybrid structure. All this modification may improve pharmacological profile, so we can obtain the analogs with stronger analgesic activity, increased stability, and bioavailability. And we can have analogs with selectivity of the site of action. So we can have centrally acting compounds or peripherally acting. So if we have improved blood-brain barrier penetration, so these compounds will we will obtain centrally acting compounds. If low penetration, we will have the peripherally acting compounds. Here, just very shortly, various strategies for searching for opioid peptides. So it is well known that activation of mu-opioid receptor produces the strongest antinociceptive effect. So for many years, researchers concentrated on obtaining analogs with high selectivity for mu-opioid receptor. But more recently, it's changed, and the development of compounds with mixed profile, like you can see here, like delta, mi-delta, mi-kappa profile, is gaining a lot of interest. Such compounds may have enhanced antinociceptive profile and causes less side effects than selective mu antagonist. And the last approach, this is obtaining of hybrid compounds, combining, for example, opioid peptides with fragments of other neuropeptides that are responsible for pain modulation, like, for example, opioid peptides and nociceptin or substance P. And now, after this introduction, that understand the idea of our research, explanation of what we do in our laboratory. So I will show you on the example of morphicaptin. We modify the structure of these native peptides. This is the native peptide by introduction of unnatural amino acids. And here you can see what we did. So instead of tyrosine, we put dimethyltyrosine. Instead of proline in position 2, we put some beta amino acids. So these are amino acids with additional methyl group, what you can see here and here, or the alanine, which is unnatural amino acids. And we change also the amino acids in position 3 with unnatural amino acids and beta amino acids. It's important to mention that beta amino acids at the time that we performed these experiments were not available commercially. So these amino acids were synthesized for us by our collaborators. This was Triman Chemicals. And why we choose this amino acid? We base on the literature and on our previous experience in our previous studies. And here you can see what we obtained. So opioid receptor binding affinities. So as you can see here we have the affinity to opioid receptor for morphiseptin. So this was our parent peptide. And as you can see, we increase the affinity to opioid receptor, but also to other receptors. To delta and kappa receptors. And we obtained some analogs with, for example, number 2. This is mostly to mi-delta profile. And for example, this is the analog with mixed profile. This is with high affinity to mi-delta and kappa receptor. Here you can see the stability, and maybe it will be better to look at this and on this slide. So morphiseptin is easily degraded by proteolytic enzymes. So this is the bond that is cut. We performed assay with DPP4. This is dipeptidolopeptidase 4, which cuts this bond. And when we change the amino acid to unnatural amino acids, these analogs were very stable. Here you can see that after 100 minutes, endomorphin, which is in red, morphicaptin, which is in red, was completely degraded. But these two analogs, I choose here number 2 and 4, were stable. We have less than 3 or 8% of degradation. We can back to the table to look at. So you can see that we have more than 90% of the initial peptide. And we check also agonist potency and efficiency. And as you can see here, we have morphiseptin, and the agonist potency of most of our analogs was higher to mu-opioid receptor, And similarly, like in binding assay, analog 2 show agonist potency and delta receptor, and analog number 4 delta and kappa receptor. So for further studies, we had to choose some analogs, and we chose analogs number 2 and 4. 2 with mix mi delta, and 4 with mi delta and kappa profile. And we try to check if this analog have the ability to penetrate the blood-brain barrier, and we use PAMPA test. This is the test in which the artificial membrane are used. This membrane mimic the blood-brain barrier, and we compare the results for our peptides to the reference compounds. So here you have verapamil and another compound, this with very high permeation, and this is very low permeation. So as you can see, both of our peptides didn't cross the blood-brain barrier. So that means that they cannot be used as centrally acting compounds. But on the other hand, we can consider them as compounds that can diminish pain peripherally. So in this case, we wanted to check the antinociceptive activity of these compounds. We use a writing test. This is the model for visceral pain. Such pain we can observe, for example, in some gastrointestinal diseases. So what we did, animals were injected intraperitoneally, or the peptides were given per os, because we performed 2 types of experiments, and after acetic acid was injected, IP. And when we inject this compound, so of course the animals feel pain, and they show the special type of behavior. We call this rights. And what we did, we calculate the number of rights. And as you can see here, in case of morphicaptin and 2 analogs, the number of rights decreased. And this was after IP injection and after per os. So oral administration resulted also in inhibition of number of rights, but only in the case of analog number 4. So when we are talking about gastrointestinal diseases, patients sometimes suffer from diarrhea. So in the next step, we check antidiarrheal activity of our compounds. So as in the previous experiments, mice were injected or administered by us with these 2 analogs, and for reference, the loperamide was used. This is an antidiarrheal agent. And after the castor oil, which is a substance with the ability to induce diarrhea, was administered to the mice, and we measured the time when the diarrhea occurred. And as you can see here, loperamide and both of our analogs increased the time when the diarrhea occurred. And when we administered per os, only analog 4 was active. And to sum up these results, so modification of morphoceptin analogs by introduction of beta-amino acid and the D-methylotyrosinine position number 1 resulted in obtaining enzymatically stable analogs. These analogs have had very high opioid receptor affinities, and it was definitely mol delta or mol delta kappa, so mixed profile. They analogs with very low BBB permeability, so their action is restricted to the periphery. So the advantage of that is the lack of central effects that I mentioned at the beginning of my presentation, so tolerance and dependence. And what we can conclude that analog 4 induced strong antinociceptive effect in writing test in mice, but also after oral administration, and inhibited diarrhea. So this new analog may be considered as interesting lead compound in the development of periphery restricted drug candidates. for example, for treatment of gastrointestinal transit disorders. Now, what we did with another study, we wanted to go deeper in GPCR signaling. So recently, the concept of bias agonists able to differently activate GPCR downstream pathways become a new approach in design of novel drug candidates. So when the ligand, here we have the opioid ligand, bind to the opioid receptors, there are two possibilities. So maybe not two possibilities, two signaling pathways are activated. So here we have G protein signaling pathway and beta arrestin signaling pathway. And activation of this pathway result in inducing analgesia. But on the other hand, activation of this beta arrestin signaling may result in internalization of or desensitization of G protein GPCR receptor. But it also can so beta arrestin also can act as signaling scaffolds. So we can divide mu opioid receptor agonists into three groups. So here we have unbiased, like morphine, which activate both pathways. Here you can see some examples. This is G protein bias ligands, which preferentially activate G protein pathway. And here we have beta arrestin 2 bias ligand, which preferentially activate beta arrestin pathway. And what are the consequences of that? So when we have unbiased ligand, so of course activation of G protein pathway results in pain relief, but activation of arrestin pathway induce side effects, which I mentioned at the beginning of my presentation. But if only one pathway, G protein pathway, is activated by G protein bias ligand, we don't observe side effects because beta arrestin is responsible for that side effects. So it can be postulated that therapeutic effect of opioids is associated with activation of G protein pathway, while the development of side effects is beta arrestin 2 dependent. So when we have the ligands either to G protein or beta arrestin pathway, so ligands with G protein or beta arrestin pathway selectivity at opioid receptors are valuable tools in the development of more safer and more efficient drugs. So that's why search for new opioid receptor agonists biased toward the G protein pathway started. And here I will show you our results. So we choose for this studies. So we wanted to check if our compounds are G protein or beta arrestin bias ligands. So we choose two compounds. This is the compound number 36 and 81. And they have very good pharmacological profile. So high mu opioid receptor affinity, high metabolic stability, and strong antinociceptive effect. And the question was if they activate both or the G protein or beta arrestin bias ligands. So what we did, so we use a breath assay. These experiments were performed in collaboration with Professor Giro Macalo from Ferrara University in Italy. And what you can observe here, so once again, we have agonist potency, maximal effect, and bias factor shown in the table. And here you have endomorphine, and so this is our parent peptide, and as you can see, both peptides were biased to G protein, but only peptide number 36 were biased to beta arrestin. This was inactive in this case. However, if we compare the maximal effect for endomorphine, we have one. Here we have only the half effect of parent peptide. So what we can conclude that one analog was unbiased, so it activated both pathways, and another was G protein biased agonist. So these analogs, which have a really similar structure, so only difference is here because we have a trifluorinated methyl group in aromatic ring, in a phenylalanine ring, can be helpful in understanding different mechanisms of opioid receptor activation and can be useful tool in search for more potent and safe analgesics. And this is the last part of my presentation. So this is just the preliminary results. What we wanted to do, we wanted pharmacological profiling of novel endomorphin 2 analogs by confocal Raman spectroscopy and imaging. So understanding the signaling mechanisms underlying bias opioid agonism is key to new drug development. However, the lack of imaging methodologies capable of tracking ligand receptor interaction and downstream signaling events in real time at the subcellular level. So, therefore, using Raman spectroscopy and imaging, we develop a new method to evaluate and understand the consequences of bias agonism of opioid ligands by providing detailed spatial analysis of biochemical components in organelles. And here you can see the peptides that we choose for this study. So here we have one analog, which is G protein biased analog, and this is unbiased analog, so number 13. So it activates similarly G protein and beta arrestin pathway. These peptides differ in pharmacological effects. So here we observe strong antinociceptive effect. It was stronger than for analog number 13 and even to the parent in comparison to the parent peptide. And there was a lack of tolerance here because it's activated only G protein pathway. Here we observed a weaker antinociceptive effect, of course, tolerance development and inhibition of gastrointestinal motility. So we can say that we observed some side effects. And the experiments, what we did. So these experiments were performed in collaboration with Professor Jakub Surmacki from the laboratory of laser molecular spectroscopy from Łódź Technical University of Technology. And if you are interested in more details, of course, I can contact with Professor Surmacki. But we decided to use Raman-based imaging technique for visualization and for comparison the intracellular behavior of this analogs that I already mentioned. So we wanted to study the biochemical processes at the cellular and subcellular levels. So how we performed the experiments. As you can see here, we had cells on Petri dish, and the cells were treated with analogs. We had also control, so the cells that were not treated. The treatment was for 30 minutes. After treatment, the cells were fixed with formalin solution and kept in PBS during the experiment. And Raman experiments were performed using a confocal microscope at 532 nanometers. Data were analyzed by simple spectroscopic methods. And here we have the results. So what you can see here, so this is Raman images, here we have Raman images with respective mean with SDR Raman cluster spectra. And in different colors, you can see cytoplasm, for example, in green, nucleus in blue, mitochondria in magenta, and so on. And on panel B, you can see the characteristic Raman bands, which reveal to the molecular features of lipids, proteins, carbohydrates, and DNA, which are associated with specific cellular organelles. And here, bar plots of the area of different cell organelles per cell area before and after supplementation of our peptides are shown. And as you can see only here in the membrane, so we observed the significant changes, and these changes were observed only for the analog number 13, which is unbiased analog, which activated both beta-arrestin and G protein pathway. And here, if you want to look, we have more detailed visualization of suitable differences in Raman band. So it's here, intensity and position. So as I mentioned, these are only the preliminary study. So we will perform much more experiments. But what we can conclude that the Raman-based imaging techniques offer a powerful labor-free approach to visualize and compare the intracellular behavior of endomorphins to, and of course, other peptide analogs that we want to study, therefore contributing to a deep insight into the spatial dynamics of G protein versus beta-arrestin-mediated mu-opioid receptor signaling. And here on the last slide, I would like to thank people from my department. So Anna, she's responsible for peptide synthesis. Karol, he's responsible for functional assays. Justina is responsible also for functional assays and for animals study. And the other collaborators, this is the Professor Jerome Macalo from University of Ferrara, from where the bread experiments were performed, Professor Alicja Kluczyk, who did the mass spectrometry analysis for our peptides, and Professor Jakub Surmacki. I already mentioned that this is the person who performed the Raman imaging experiments. Thank you very much, and this is the city that our university is localized. So this is Lodz city. Thank you for the opportunity to present our results.
Dr. Jansa, the experiments are very interesting and the results are having a very nice potential, it looks like. Thank you very much. Is there any questions or query from the audience?
Hi, Professor Kat, are you listening?
Hello.
Are you listening to me? I'm Sudhanshu Tripathi.
Yes, I'm listening.
I have a question for you.
Yes, of course.
Can your drug, you feel, be used for non-narcotic analgesic or narcotic one with minimum side effects?
So we try to obtain, so there are two possibilities. If we obtain the centrally acting compounds, we try to obtain the compounds that relieve analgesia, that induce analgesia, but without tolerance, without addiction. Yes, we try, because you know that the addiction is also mediated through the beta-arrestin pathway. So we try to obtain the analogs that will be only a G protein bias. In this case, we will have the peptides, the analogs that only induce analgesia without side effects.
So thank you very much. Thank you very much for participating in this. Thank you. Please go ahead.
Next, we are privileged to welcome Dr. William Bogging Fitzio, Senior Lecturer at the University of Douala, Cameroon, and a distinguished researcher in applied spectroscopy. Dr. Fitzio is an accomplished scientist whose journey is both inspiring and impactful. He earned his master's degree in theoretical molecular physics in 2010 from the University of Douala, followed by a PhD in applied spectroscopy at the University of Tunis al-Manar, Tunisia. His research stands out for his motivation and social relevance, developing low-cost, practical spectroscopic methods that bring powerful analytical tools to laboratories with limited resources. From food quality testing to engine lubricant analysis, his contributions bridge science and society. Along the way, he has been recognized with honors such as the C.V. Raman Scholarship from the Government of India, and his work has been widely published in reputed journals. Today, Dr. Fitzio will present his pioneering work on low-cost spectrophlorometers for engine lubricant analysis, showing how affordable tools can deliver accurate, practical solutions. Please join me in giving a big round of applause to Dr. William Bogging Fitzio for his talk on low-cost spectrophlorometric analysis of engine lubricants using chemometric tools. Thank you.
Well, thank you. Thank you for giving me this opportunity. I'm actually facing some internet issue. I don't know if you are hearing me.
Yes, sir, we are hearing you.
So, are you having a view on my slide?
Yes, sir. Yes, sir.
Okay. Well, thank you. Thank you for this opportunity. I would like to thank, first of all, Professor Ashok Kumar Mishra, Professor Abani Sao, and the whole organizing committee for this invitation. So my presentation is focused on a laboratory design spectrophlorimeter for the characterization of engine lubricant. Well, when we talk about optical spectroscopy, we in our research group, we are mainly using optical spectroscopy for sample analysis in the domain of quality control. Usually it can be food sample and or other type of real life sample. So optical spectroscopy method have been used, for example, infrared, UV, fluorescence, and so on. This is because normally, standard measurement or standard method for the analysis of such sample are sometimes very expensive and they require, for example, skills experimentators. So, actually, optical spectroscopy, which is advantage, which are usually, for example, low cost, high sensitivity, and the fact that they do not require skilled scientists are usually actually encouraged. So, in our case, we are mainly focused on fluorescence spectroscopy. You will see that nowadays there are several instruments for making a fluorescence measurement. Those instruments can be found in different companies. We have, for example, Ocean Optics, Jobin Yvon, for example, Perkin Elmer, and so on. But there is a problem. In developing country, which is, for example, my country, precisely I'm in Cameroon, we usually have an issue which is the lack of facilities because the state will not really provide fund for research laboratory. So in research laboratory, instead of having standard equipment for fluorescence measurement or for other types of measurement, we will find some specific individual equipment or element which in turn, if you put them together, may allow you to produce good result as standard equipment. So our aim here is to present how, by using low-cost material from optics and spectroscopy, we were able to design a spectrophlorimeter. On the other side, how we use this spectrophlorimeter to characterize engine lubricant. So the plan of the presentation is this: a small rappel on fluorescence spectroscopy. We will talk a little about engine lubricant. Then we will end by presenting the result. Fluorescence is just the emission of light by an entity, which can be a molecule or an atom, which has initially absorbed light. So on this figure, for example, you can see the fluorescence of an essential oil. We have the blue or the UV light, which here looks like blue. The wavelength is 365 nanometer, which is used to give or to produce or to excite the molecule in the essential oil, and the response is this green fluorescence. The phenomenon of fluorescence was discovered in 1565 by Monad, and the Stokes is really the scientists which make it to be well known. By using the so-called Perrin-Jablonski diagram, it is usually easy to explain on, let us say, quantum point of view, the fluorescence emission from a molecule. You will have, for example, here, the different energy level of a molecule, the single state, which is the fundamental state, and the different electronic excited state. So upon absorption of a radiation of light, the molecule will undergo a promotion toward the excited electronic state, may undergo internal conversion, vibrational relaxation, and then from the first excited electronic singlet state, precisely the lowest vibrational state, can produce fluorescence. But when we are dealing with the type of sample that I mentioned previously, for example, which is food samples, engine lubricant, usually they are not only composed by one or two molecules, they are a mixture of several molecules. It means that by using just a single excitation wavelength to obtain the fluorescence spectroscopy, or to obtain, sorry, the fluorescence spectrum, we can miss important information. So to solve that issue, Johnson and co-worker in 1977 developed what is called now excitation emission fluorescence matrix. On the figure on left, I have a small example on how it works. Let us say that molecule A and B are found in a sample. You will see that if we use, for example, a radiation of wavelength energy E1, the red one, we cannot have any fluorescence information. If you use E2, we can have a good information on the fluorescence of molecule A, but not on the one of B. But if we use the last excitation, E3, we are sure that we'll have fluorescence of both molecules. Nowadays, there are several standard equipment to record fluorescence spectra. On the right side, for example, we have some images. We have, for example, the Aqualog for Jobim Yvon. We also have the LS50 for Perkin Elmer, and so on. Now, let us talk a little about engine lubricant. Engine lubricant is a product derived from mineral oil, which also is a product deriving from the distillation of crude oil. Engine lubricant have a good aim or have different aim when we talk about engine. They have been used, for example, to reduce heat, to reduce friction. They have been used to fight against corrosion, and so on. They are very useful, or I will say that they are unavoidable when we are talking about engine. And in the domain of engine lubricant, engine are gathered in terms of classes. For example, there are engine lubricant which have been used or which are used for gearboxes, some which have been used for engine, and others which have been used, which are used for two-stroke engine. So it means that we cannot use, or we should use, the appropriate type of engine lubricant for the appropriate engine. But in countries like mine, developing country, actually there is a problem. The problem is that those lubricants are already sold on the street. It means that you will not see them only in station. You will find them on street, and on street, they don't really have any identification. You who want to buy, you cannot really identify them correctly. So we faced some problem recently because people were complaining about the fact that their engine were not working well, and a study showed that this was the fact that they were using inappropriate engine lubricant. So it is very important to develop a method which can allow us to really identify the engine lubricant that is being used, or to say that if this is a transmission lubricant, let us confirm that this is effectively a transmission lubricant. So in this study, 14 samples were considered, and they belong to three classes: two-stroke engine lubricant, motor lubricant, and transmission lubricant. We also have the chance to be provided for those samples with some physicochemical parameter, including kinetic viscosity, pour point, viscosity, and flash point. So let us now go to the result of our research. The first point is the design spectropluorimeter. This is a schematic view of the design spectropluorimeter. The excitation compartment is composed by an arc lamp from Abed Technology combined to a manual monochromator from Jobin Yvon. The excitation light after the excite slit of the monochromator is focused by two lens to the extremity E1 of the first leg of a Y-type optical cable. That leg is composed by 6 fibers, which bring the excitation light toward the sample contained in a cuve in the sample chamber. From there, the fluorescence will be collected by the E12 extremity of the cable, which is composed by the previous 6 optical fiber with 1 fiber in the center. That fiber will collect the fluorescence and bring it toward the second leg of the Y-type optical cable toward the spectrometer, which is here a USB 2000 spectrometer from Ocean Optics, connected to a computer for the spectrum recording. So after designing the spectrometer like this, the next step was to define the protocol used for recording, to record a matrix or excitation emission matrix. So here are the main steps to record such spectrum. So in the step 6, an important point is how to make spectral correction. Spectral correction are some artifacts which are inherent on any spectroscopic equipment. The main artifacts are the sensitivity of the camera used to record the spectra and the bias of the excitation source. So here, for the first problem, which is the sensitivity of the camera. The sensitivity of the camera is the fact that the camera will not count incoming photon with the same efficiency. This is also like human eyes. For example, in daytime, human eyes has a peak or a maximum of observation in the yellow-green region. So here we have in the relation 1, which gives us information about the fluorescence of a molecule. But when this fluorescence is collected by the detector, it is affected in relation 2 by what we have called here C lambda, which is the sensitivity of the camera. It appears that to have the good or the corrected spectra, we may have GC. GC when you are using a standard equipment is given by the manufacturer, or sometimes you can use radiometric lamp to obtain them. In our case, as we didn't have such element, we were supposed to develop a new method. The new method took advantage of the Oceanoptics software spectra suite in its ability to evaluate or to compute the spectrum of a black body source of light, knowing its color temperature. So the spectrum or the experiment is the following. In the sample chamber, we will place an incandescent light source lamp, and we will collect its signal or record it with the USB 2000. The relation tree shows us that the actual true spectrum called T is affected by the same C artifact of the camera and give us L, which is what we read with our computer. So to obtain C is just to make a ratio between L and T. Remember that T will be provided by our software, provided that we know the color temperature of the light source. So we make this experiment not only for our USB 2000, but also with another spectrometer, the USB 4000. And here we present the result. In A, we have the fluorescence spectrum of an essential oil, for example, recorded with the two spectrometer. The blue curve is the spectrum obtained with USB 2000, and the black one is the one obtained with USB 4000. Of course, the shape and even the so after correction, please a moment. I'm facing some internet issue. So after correction in B, we can see that the corrected spectrum are the same with a correlation coefficient of 0.9. So it means that the obtained response or the obtained sensitivity or the obtained coefficient, correcting coefficient for each camera are good, so that whatever we will record with those spectrometer, we will just need to divide them by the C, the function C obtained. Next, the correction of the artifact from the excitation compartment. As we said it, the combination of the light source and the monochromator will not give the same intensity of light for each excitation wavelength. We can see it by the presence of A0 here in red. So to deal with that issue, again, with standard equipment, there are solutions. For example, the use of a quantum counter, which is usually a saturated solution of rhodamine. But again, in our case, we develop another approach consisting in recording the spectrum of each light corresponding to each excitation wavelength. We can see in the relation 5 that what is read with our computer is just the product of what is true, is 0, times with the correction or the artifact of the camera. As we already the function function C, we just C to obtain E0. Now, each spectrum obtained with the corresponding coefficient. And the final correction to make when dealing with excitation emission matrix is the Rayleigh. The Rayleigh does not bring any analytical useful information, and it is the manifestation of photon which are collected by the detector at the same wavelength as the excitation. So here, for example, in A, we have the Rayleigh, and in B, we can see that the Rayleigh is no longer there. Here, we use the method developed by Barham and co-worker, which consisted to define a range of wavelength where the Rayleigh is found, allow it to be missed or remove all the points, and then make an interpolation. So with this step, we can now be able to record useful excitation emission matrix that can be used to have important information. So our sample presented previously were used in our experiment, and we can see here, of course, here, for example, is what we made because as we are doing everything manually, we develop a module by using the software Ego, which can allow us to have a gain of time. So yes, so we can see here, you can see here the interface of the module, which allow us to compute or to plot excitation emission matrix spectrum. So here we present, for example, excitation emission matrix of some samples of lubricant. So we can see that we have, for example, emission which we have identified them as A, B, C, G, E. On the second plot matrix, we have a new emission F. So this is what we call excitation emission. We have here the emission axis, and on the left, excitation axis. So those peaks represent the emission that we can find in the lubricant. They are the response of molecules which are actually giving the fluorescence of the sample. Now, the question was, so as we have made it, what can be the most efficient excitation wavelength that we can use to have a maximum information on engine lubricant? To do that, we took advantage on chemometrics method, precisely principal component analysis, which is a reduction method. And to apply PCA by using the cube of data, the cube of data is the three-dimension cube consisting in excitation, emission, and sample. We unfold it on the excitation wavelength and then use it as input for PCA. So here we can see the corresponding or the obtained score plot. So we consider that the efficient excitation wavelength will correspond to a change of shape in the matrix. The correspondent, or it will correspond now on this plot to wavelength where the shape or the presentation of point will change. So here, for example, we can identify the wavelength, for example, here in the rectangle 350, 400, 450, 470, 300 as the most efficient excitation wavelength when you are talking about engine lubricant. The next question was, as we have identified this excitation wavelength, what is the profile or the individual profile of the molecule that may emit or which are actually emitting fluorescence in our engine lubricant? Again, We took advantage on another chemometrics method, which is parallel factor analysis. It's a method based on the B-Lambert law. So by using that method, we were able to extract the individual excitation and emission profile of potential fluorophore in engine lubricant spectra for emission. Of course, a centrum may correspond. This is sometimes a very difficult task when we are working with real-life samples. So it's not always easy to identify, but here, by taking advantage of chromatographic information about molecule present in engine lubricant, and by using some a table of fluorophore, we were able to identify two of these components as fluorine and pyrene. Now, our final uh, let us say, objective here was, as we were provided with physicochemical parameter, which fluorescence peak can be used to give information on a corresponding physical. Again, we use here the combination of parafac and PCA. The score obtained with the method parafac were used together with physical-chemical component as input for the PCA analysis. So here we present the login plot. On this login plot, you can see that most of the physical chemical were very far from the fluorescence component. Only component 1 here in the fourth area of the cycle, the fourth quadrant, component 1 seems to be close to viscosity. So with that, we end the presentation, which consisted to show you how, by using cheap basic material from optical spectroscopy, we were able to design spectrofluorimeter, which was used to record or to characterize engine lubricant. And here are some output obtained with this equipment. For your kind attention, thank you very much.
What is that? William, can you hear me?
Yes, sir, I can hear you.
Okay. So, is there any question from the audience? So, thank you, William. Your presentation was good, and your work was very interesting. This is a little older work, isn't it? Okay.
Yes. It's the older one.
I see. Okay.
I
So
thought
wonderful
that
talk.
according to the aim of the international school, it may be much more interesting to present it.
Oh, it was interesting, really. Thank you very much.
Yes.
Thank you.
Thank you. Thank you, sir.
Now it is our honor to welcome Professor Dr. Harikrishna Sahu from the Department of Chemistry, NIT Rourkela. Sir is a former guest scientist at the Max Bergman Center, Dresden, with 13 plus years of teaching experience in chemistry and spectroscopy. He has published over 80 papers, authored book chapters, and reviews for leading journals. He is a recipient of international fellowships from RSC, DAAD, and NAWA. His research focuses on biophysical chemistry, particularly understanding protein denaturation, renaturation, aggregation mechanisms, and the impact of environmental stress. May we now request Dr. Harikrishna Sahu to present his talk on the impact of micro and macro environment on protein conformation and dynamics. Sir, please.
Okay, thank you. My special thank to Avani sir who invited me to present here my work, and I hope still all of you have some energy for next 20-25 minutes, and I will try to finish up within 20-25 minutes. Okay, so today I am going to tell you about the applications of optical spectroscopy, specifically fluorescence and circular dichroism spectroscopy, how we use that to decipher the protein conformation in a crowding environment. Okay, so why we are going to use this crowding environment, what is the use, that I will tell you. So first of all, like when a protein that gets synthesized from the ribosome, then it goes to directly to the native state, which is the functional state, and always the protein which is not in the functional state, that doesn't function properly, and then we have many problems. Okay, so the most important thing is that the protein should be in the functional state, and in the meantime there are some factors which may impact or may affect the protein in order to go to non-functional states like misfolding states and then the aggregates. Okay, and once it aggregates, it becomes toxic to the body, and gradually either it degrades or it can be like get out of the cells. Okay, so what are those factors which affects this aggregation process or the denaturation process of the protein or makes it non-functional? So there are like temperature, pH, then your microenvironment or salts, then you have the crowding agents and molecular chaperone or catalyst. Sometimes they are very useful to bring down the proteins to the functional state always. And then some small molecular mass molecules like you have nascent protein peptides or some amino acids which are the byproducts of some like biological reactions inside the system. Okay, so the next thing is, as I told you, it is very important to see the protein function in the crowding environment. Okay, so why? Because when you go to the cytoplasm in the cell, it is not the protein which is alone in the system. Okay, so it is like surrounded by many biomolecules, like your salts are there, carbohydrates are there, other proteins are there, nucleic acids, so many things are there. So now you think about, if I will be alone inside this room and then when I will be with the crowd, it is a completely different scenario, because I need to interact. Okay, so similarly, when your protein is inside the crowded system, that also tries to interact with other proteins. Okay, and that way the folding and unfolding dynamics, that also differs. Okay, and if we go more towards the what are the crowding environments are present in the system. For example, you can see like you have chromosomes, ribosomes, then polysaccharides, lipid proteins, so many things are there. So this is inside the cell, and then we have another section where between the cells, that we are calling it as extracellular matrix, which is the between two cells, and that helps in signaling process between one cell to another cell. There also, if you see, it is not only the proteins, there are like lot of other things, like the modified carbohydrates like hyaluronic acids, then you have sulfated, non-sulfated, other proteins, receptors, so many things are there. So it is very, very interesting, or it is also required to study the the target protein, how it behaves in the crowding environment. Okay, so for that reason, what we did, of course one can go with the proteins, other proteins, but we have like n number of proteins. So if I take one protein, which protein I need to take as the crowder? So it is for that reason what we decided, like we will go with some like traditional or conventional crowders, and for the cytoplasm as well as for the extracellular matrix. So in this case we have used this polyethylene glycol, cyclodextrin, then dextran, fical for the cytoplasm, whereas glycosaminoglycan, which is present in the ECM, we use that as the crowder. Okay, so then another reason also there, if we see the cytoplasm, it is not equal size of the crowders, they are like different sizes, and then also strain molecules are there, flexible materials are there. So on that basis we have decided the polyethylene glycol, which is flexible, cyclodextrin, it is constant, rigid, then again dextran, in order to compare the cyclodextrin and dextran, because one is this linear, another is a cyclic one, and then fecal, which is neutral one, and glycosaminoglycan, which exactly mimics the extracellular part. So today I will show you only I think one part polyethylene glycol on the basis of ensemble measurement, as well as in the single molecule also, which we did in collaboration with Professor Klaus Seidel from Germany, and a bit of ensemble results from cyclodextrin also. Okay, so now the point is the protein, because that is also you need to choose such a protein that which is very, very resistant to the other factors. Okay, so for that reason we selected a small protein which has only 117 amino acids, that is CREBP, cellular retinoic acid binding protein, and the major function of this protein is that it binds the retinoic acid, as retinoic acid is not available in the cytoplasm, and then it transfer it to the nucleus for our optical processing inside, like during the genetical level. And as you see, it has like major structures are beta strands, and only 15% of the protein is of helical structure. So this is the helical structure, and these plate like structures are the beta strands, and it is very, very stable, as it is a barrel-like structure. Inside there is a cavity, so it is also included in the beta barrel family. Okay, so this is the function which I already mentioned you. Okay, now how we can correlate it to the fluorescence? As I told you that in this case we have applied the optical spectroscopy. So there are two ways. One is almost all, I think 99.9%, and I think Ashok sir is also going to like say yes, that 99.9% of the proteins, they have some intrinsic fluorescence, and that comes from the aromatic amino acids. There are three different types of amino acids. One is tryptophan, tyrosine, and phenylalanine. And out of these three, one is very fluorescent because of its high quantum yield, that is tryptophan, then tyrosine and phenylalanine. In most of the cases, tryptophan and tyrosines are tracked to see the behavior of the proteins. Okay, phenylalanine, it has very less quantum yield, still it has a fluorescence. Okay, so in our case we have three tryptophans. That is also problematic because you do not know which tryptophan has the fluorescence. Okay, so the beauty of this protein is that it has three, although it has three tryptophans, two tryptophans, this 7 and 109, they are buried in the cavity. So whenever there is a change in the solvent, the first one is to go with the 87. So 87 will be interacting with the solvent more like prominently than your 109 and 7, because the solvent cannot go to 109 and 7 as they are like you can say that they are captured inside the hydrophobic core. Okay, so now let's come to the results. So first of all, when we study a protein, its dynamic, it is better to see whether it is reversible or not. Okay, so the first is that circular diachrosm, where you see this is a very traditional pick for the beta sheet proteins, and sometimes some proteins, they have their own characteristic properties. Okay, so for CRBP there is a peak downward peak at 231 nanometer, and this is the characteristic peak at 216. Okay, and from the fluorescence also it is very clear that if you like unfold it, not unfold it, if you denature it and then you try to denature and renature, coming back to the native state, it comes back to the normal state here. Only the intensity difference is that when you unfold it, it goes up because the tryptophan's conformational changes in the system, and then the renatured, the red one is like less compared to the denatured, because we denatured the protein in presence of urea, and when you renatured, we diluted the protein because it is 8 molar urea. So we diluted the protein to almost like 0.1. So that's why the intensity of the protein decreases, but if you see the wavelength, it is almost at 326, whereas the denatured protein has around 350. Okay, so this shows that the protein is well, like it can be like brought back to the folding state. Now first I will go with the ensemble measurement. Okay, so as I told you that we have like this different macromolecules we have used, and all those macromolecules, they are based on the structure, shape and the concentrations also. For example, P is polyethylene glycol. We have studied like there are 5 different shapes, like depending on the molecular weight, 400, 1000, 2000, 4000, 8000, and also in the next slides I will show you that different concentrations. Then you have cyclodextrin, that you can see it is a constant strain molecule, fecal and dextrin, and we have like already some of the publications on the same crowding environment. Okay, so let's start with the polyethylene glycol. So here before going to any of the temperature, pH, any measurement, first we need to see whether the protein is stable at the room temperature in the presence of crowding environment or not. So in order to check that, we went with the secondary structure investigation, and in secondary structures we see that there is not much change, almost there is no change, I can say. So this means the protein is very, very stable at room temperature. Okay, so then only we can go to different chemically denatured states or high temperatures to have a look on that. Okay, and from this the urea melt, what is urea melt? Like when you increase the concentration of the urea and then you track the fluorescence of the tryptophan, so gradually when the protein gets denatured, the tryptophan goes out, okay, and then the fluorescence changes there. So that you can track in order to see at what stage the protein completely gets unfolded or denatured, okay, and from there you can calculate the CM values, which says that 50% of the protein is in the denatured state and 50% is in the natural like native state. Okay, so now the point is, when you compare without PEG, polyethylene glycol, then 2000, 4000, 6000, in all of the cases the black one is for the protein without the polyethylene glycol, and rest are in the presence of PEG, and everything that shows a right side shifting. So what is that? So this means that in order to unfold the protein you need more urea, means it stabilizes the protein at room temperature with respect to the denaturation experiments. Okay, and yeah, so next, so this is what intensity diagram. So this is with respect to the fluorescence intensity, and this is with respect to the wavelength, because for this protein the native state, if you have remembered, the native state has 326 nanometer, and when it is unfolded it has 350 nanometer as the maximum. So there is a huge gap with 24 nanometers. So that also we try to track, and we thought to compare whether both are correct or not, because sometimes intensity can fluctuate with the intensity with the concentration, but your wavelength will never fluctuate. So you can see that the plot or the data here, they are very, very like well aligned with the fitting line, whereas in the intensity you can see there is a fluctuation of the intensity, and there is almost no difference with the CM values between these two. Okay, so from here one can say that these polyethylene glycols, they usually stabilize the protein from the CM values from the urea melt. Okay, now again it does not mean that they also stabilize during the kinetics, because kinetics is different, room temperature experiments are different. So when you go to the kinetics, it is a reverse one. Okay, so now when you compare the kinetics at for this 2000 polyethylene glycol, and it is 40 grams per liter at different urea concentrations, you can see that the black line is 5.5 molar urea, and when you increase the concentration of the urea, PEG 2000 is not helping much. Okay, there are two things: when we increase the urea concentration, the denaturation process will increase, so that also the rate will increase, because we are increasing the urea concentration. So what we thought, as it is stabilizing, it may hold it back, okay, and the rate will not increase, but this did not happen. Okay, so this means at a particular stage the stabilizer is also not stabilizing the kinetics. Okay, so then we thought, let's keep the urea concentration constant, change the concentration of the stabilizer. So that is what we did here: 5.5 molar urea and 7.5 molar urea, and then we went with different concentrations. One is I think 80 grams per liter PEG 4000 and 100 grams per liter PEG 2000. In both the cases they stabilize here. Okay, so this is the red, black one is no polyethylene glycol, red one is your 2000, blue one is the 4000, and now it shifts. So the rate is decreasing, means they are stabilizing the the protein. So they do not allow the protein go to the denatured state. And the same thing also at 7.5 molar urea, where most of the proteins are in the denatured state, but still these two stabilizers they bring it back. Okay, so this is what we got it from the kinetics, and then when we plot the unfolding kinetics with respect to urea concentrations, there we saw two different things. The first one is this is 2000 and I think both are 2000 in different concentrations, so the slopes are almost same, but when you go to 4000 then the slopes are different. So this means when the slopes are different for the unfolding kinetics, if the mechanism of interaction between the stabilizer and the protein are different, in those cases the slopes will be different. Okay, so from here we can roughly, or not roughly, we can confirm that both 4000 and 2000 they act as a stabilizer in the unfolding kinetics. Okay, then what about the refolding? Okay, so as the protein is refolded, then what are the impact of this 2000 and 4000 polyethylene glycol on the refolding kinetics? In the refolding kinetics we considered like two different concentrations, one is 6 molar urea and another is 8 molar urea, and 400 then 1000 400 1000. Okay, and different concentrations are there in both the cases. Almost in this one I think it is 400 and this is also 400. There is not much difference with the 6 molar and the 8 molar urea, but in case of 1000 there is a little change. You can see that it makes it faster. The refolding also makes gets faster in the presence of the polyethylene glycol 1000. So it stabilizes in the unfolding part, and in the refolding it helps it to refold faster. Okay, yeah, renaturation. So actually the unfolding term is not correct, because unfolding means it is completely loses the structure. Yeah, exactly. So this will never happen, and if happens then we need to go to the Leventhal paradox. It will take years to refold again. So better word is the denaturation. Okay, so during the renaturation and denaturation, in both the cases this stabilize the polyethylene glycol that helps the protein in a good sense. Okay, sorry. Yeah, so this is again the comparison in different Crowders like 2000 and 4000. In both the cases similar type of results we are getting like 1000. So this is what we got in the ensemble. Ensemble means like all the different types of proteins, like same types of proteins but different conformations are there. So how to separate them out? So we can go with the single molecule technique with that. So where we can see that how much from one conformation is present. Okay, yeah. So for the single molecule it is the fret mechanism already, like there are lots of theoretical background is we have seen. So in this case we need two fluorescent dyes, and as tryptophan is not a good tracker in the visible range, that's why we need to use external dyes. So here we use the green one is Alexa 488 and the red one is Alexa 647, and always there is a trick that where to label the protein. Okay, so the point is we have used these two external positions where these dyes are not going to affect the structure of the protein. That is also very important, because if I want to put it here, then it will break the protein, because of the size and then the interactions, everything, it will like damage the protein. So that is what we use this K21C, which is the external. So here is the red one, and then D104, these 2 points, and here we attached Alexa 488 and here we attached Alexa 647. So they are a very good fret pair. Okay, now from the fret results, so as we have labeled the proteins in the native state, high fret is expected in the native state, and when there is no fret or low fret, this means they are going away from each other. So these 2 points, when they are close, high fret, when they are moving out, then it is low fret. Okay, so low fret means there will be no energy transfer from donor to acceptor. Okay, so if there is no energy transfer from donor to acceptor, means the lifetime of the donor will be high, because donor is losing nothing. Okay, so from there, this is the native state, where you can see that it has almost 95 to 99% conformation at a particular spot or particular conformation. Okay, and there, this is the lifetime of the donor, and it has a maximum of 4 nanoseconds, but in native state it is almost like 0.9 nanoseconds. So this means almost all the fluorescence energy is transferred to the acceptor. Now gradually we went with different urea concentrations. So this is 0.5, then 2.5, 3, 3.5, 5.5. In all those cases, you see gradually it is expanding. So this means the structure is trying to go out of the native state. So that's why there is a spread here, and gradually the spreading is also increasing, and finally there are 2 spots are coming. One is in the native, another is in the non-native state. This is the completely non-native state, which has 4 nanosecond and no energy transfer. Okay, and when you increase the urea concentration, gradually it goes out, it vanishes. So this means there is nothing native state, all are from the non-native state or denatured state, we can say. Okay, so this is from the urea urea results what we received. Then our job is to try the polyethylene glycol, how they are impacting. So this is the native state, 3 molar urea, 50%. Now you go to 2000, you see there is almost very less spots are there at non-native state, and everything goes back to native state. And also same thing is happening at the 4000. There is almost no spot here, and everything is in the native state. So this means those conformations which are in the denatured state, in the presence of this Crowder, that brings it back to the native state. We have seen that in ensemble measurement. Now in the single molecule also we have seen that. So what happens when the retinoic acid is there? Because its function is to transfer the retinoic acid from the cytoplasm to the nucleus. So that also we have seen here, that this is without the retinoic acid, single spot, but when the retinoic acid is there, it's little, it's trying to, the arms of the protein are in a little bit dynamic mode. That's why you have a little spot here. Okay, and when you put PEG 4000, it is like 1 spot, but there is a little in the non-native. So here you have 2 spots in the urea case, means 50-50, and in presence of retinoic acid, 3 molar urea, this is major, means the unfolded is major. So this means the dynamic nature is more, but when you have 4000, again it come back to the native state. Okay, so this means it makes the non-native to native here in presence of the polyethylene glycol 4000. Okay, so this is what the role of the polyethylene glycol towards the denatured state of the CRBP. Okay, so it's a very good friend of the protein. Now, what we thought, let's try with the cyclodextrin, which is a very compact one. What does it do? Okay, whether it stabilizes or destabilizes. So, from the CD structure, as I told you, always we need to try whether the secondary structure of the protein changes or not in the presence of analyte at room temperature. There is not much change here, we can see. And yes, here also when you increase the concentration from 0 to 90 micromolar also, there is not much change. Okay, but when we go to the kinetics, there is a huge change here. So the beauty is that you have the 0 molar in the middle. Okay, one part is increasing the unfolding rate, another part is decreasing the unfolding rate. The lower concentration is increasing the unfolding rate, the higher concentration is decreasing the unfolding rate. So it has a mixed behavior. Okay, so then what is the concentration? Where exactly it has the 50-50. Okay, so to that also in refolding there is not much change between 40 and 80, but it has a change from the native, that it increases the refolding rate. Okay, but here it has dual factor. And then we try to go with a little step size of the concentrations starting from 0 to 25, because in the last one we saw that at 40 it is increasing, at 80 it is decreasing, and when we went with the 0 to 25, we saw that till 25 it is increasing. Okay, so 25 25 till 25 it is increasing, and till 40 it is also increasing, because in the last one I showed you that 40 it is increasing, and refolding also same thing. And the reason behind why we went to 25, why we could not go beyond that, because our prime aim is to compare alpha, beta and gamma, and the concentration of the solubility of gamma is very less compared to alpha. Alpha you can go up to 150 micromolar, but gamma you can go only 25, and that is the reason why we restricted ourselves at 25 micromolar. Okay, so yeah, and then we went with beta with 1 unit increase, and there also we saw that at lower concentrations it increases the unfolding rate like alpha CD. So most probably what we saw that in case of cyclodextrin, it has a dual factor. One is in the lower concentration, another is the higher concentration. Okay, so from all this what we can conclude that it has two natures. One is in positive effects, another is the negative effect. From the positive effect, what it can do, it can stabilize the native protein, what we saw, and then also it can increase the protein-protein interaction sometimes, which is very helpful for the biological functions. And the negative impact is that it decreases the activity through different phenomena. One is like hydration effect, then excluded volume, and your increase in the viscosity, because when the viscosity increases, the expected dimerization cannot happen, and movement also that get restricted. Okay, so these are all from the crowding effect, and these are like some other research works for what we are doing in the lab. Like I told you that the protein aggregation can happen. Okay, so or the misfolded protein that can go to aggregates. So the biggest question is that if the protein aggregates, can it be brought back to the native state? This means the disaggregation. So if we can do that, any protein which goes to the aggregation, we can immediately bring it back to the functional state, and we succeeded with that by using ionic liquids that act as the disaggregating agents for these proteins. Yeah, so I think we use this ammonium ionic liquid for the disaggregating to deaggregate the aggregate proteins. Okay, and there is another stuff also we are doing this nanoparticles and how we can use the nanoparticles in mimicking the biological environment. And yeah, so these are the small groups. One is aggregation, then crowding, and small molecular interaction like protein drug interaction, protein other molecular small molecule interaction, and biomaterials which are also we were working, because one point is that when the protein aggregates it is useless, like it cannot be used anymore. So if we can take that aggregate and we can make some biomaterial that can be useful, so that is also we are like running now. Okay, so these are all the people who are working, and I am the one who is moving here and there like traveling and funding agencies. And these are some beautiful snaps from our campus. And before I leave, one announcement is that in December we are organizing the OCS annual function on 21st, 22nd, 23rd of December. So you all are welcome there. Thank you. Any questions, please? Yes. Thank you, sir.
So PEG polyethylene glycol easily we can synthesize, and we can describe all the folding concept and refolding portion and naturation, denaturation, but the same concept that we can apply in cyclodextrin and dextrin also. As like Ficol is deactivate, you also show that like in it, but cyclodextrin is same applicable concept regarding folding and refolding and protein synthesis, same process apply on that.
Yeah, so there is a difference. Why cyclodextrin has dual effect? Okay.
Yes, sir. Alpha, beta, and gamma, different kinds of cyclodextrin.
Because always, like when two molecules are coming together, either they have non-specific binding or they have specific binding. Where they have specific binding, the behavior is different. When there is non-specific binding, there is a different behavior. So most likely, as the polyethylene glycol is a neutral molecule, the interaction is non-specific, what I think. In some cases for cyclodextrin, there is a specific hydrogen bonding interaction might be possible with the outer rim where you have the secondary alcohol CH2OH. So that could be the reason why these two are showing different functions.
So PEG flexible compound also, that's maybe the region that
PEG flexible.
Yes, sir. Cyclodextrin look like hearts, and the surrounding parts are like different kinds of small atoms are exaggeratedly correlated with. That's the helical like structure, so that cannot be easily flexible for easily combination and folding refolding. That's why PEG is essential.
And also sometimes what we are expecting that in case of cyclodextrin, as it has a cavity,
yes, sir,
the amino acid side chains can partially be there, not completely, partially, just with the upper rim a little bit maybe. So that has to be studied in details.
So that's why PEG is most prominent for basic research now, I think so.
Yes, why not?
Thank you. Thank you, sir. Thank you.
Thank you, sir. Now we request Dr. Ashok Kumar Mishra, Dr. Abani Kumar Sahu, and Dr. Deepa Nag to felicitate Dr. Hari Krishna Sahu.
As we reach
ऑन कर इधर से
As we reach the close of today's proceedings, it gives us immense pleasure to look back on the remarkable sessions that we have witnessed. From fundamental insights to modern applications, today's talk have taken us on a fascinating journey across the many dimensions of spectroscopy.
Indeed, what made today so impactful was not just the science but the vision that came with it. Whether it is unveiling molecular structures, detecting pollutants, or advancing medical diagnostics, spectroscopy is truly a bridge between research and real-world solutions.
As day one concludes, let us carry forward the spirit of curiosity, collaboration, and scientific inquiry into tomorrow's session, which promise to be equally inspiring and thought-provoking. With these, we officially bring the proceedings of day one to a close. And we request all the students to reach at 8 a.m. sharp tomorrow, finish their breakfast, and be seated at the hall before 9 a.m. We would start tomorrow's program at 9 a.m. Also, we are eager to announce that tomorrow, after the validatory session, interested student can perform cultural activities such as dance, drama, song, etc. Wishing you a pleasant evening, and we look forward to welcoming you again tomorrow. Thank you.